Some of the most important questions in archaeology do not begin with the discovery. They begin with a contradiction, a remote site that required enormous resources to build. A settlement that flourished where survival should have been difficult. A structure that remained in use for centuries despite dramatic political and environmental changes around it. Again and again, the ancient world presents situations that seem to challenge expectations. The evidence is real. The ruins are real, yet the reasons behind them often remain uncertain. That is what makes ancient mysteries so compelling. They force us to look beyond what was built and ask why it was built, why it lasted, and why its story was eventually lost. Sometimes the greatest mystery is not the monument itself, but the decisions that created it. Anglesey, a windswept island off the northwest coast of Wales, contains one of the most remarkable concentrations of prehistoric monuments in Britain. Long before written history reached these shores, its inhabitants aligned stone chambers with the sun, transported multi-ton blocks across difficult terrain, built durable settlements without mortar, and developed technologies whose underlying methods remain only partially understood. More than 5,000 years later, some of the most important questions about how they achieved these feats remain unanswered. Although local monuments were known for centuries, systematic archaeological investigations accelerated during the 19th and 20th centuries. Excavations at Bryn Celli DDU, Dinlligwy, Barclodiad y Gawres, and numerous other sites revealed that Anglesey was not an isolated prehistoric community, but a major centre of engineering, ritual activity, metallurgy, and knowledge transmission spanning thousands of years. The most famous mystery on Anglesey revolves around Bryn Celli DDU, a Neolithic passage tomb constructed around 3000 BC. At first glance, the monument appears simple. A stone-lined corridor approximately 8.5 meters long leads into a burial chamber covered by an earthen mound. Yet modern studies have demonstrated that the passage is carefully aligned with the sunrise during the summer solstice. For a brief period each year, sunlight enters the narrow entrance and penetrates deep into the chamber, illuminating the interior with remarkable precision. The achievement becomes far more impressive when viewed through an engineering lens. The builders possessed no compasses, telescopes, written mathematics, metal surveying instruments, or modern measurement systems, yet they created an alignment accurate enough to function more than 5 millennia later. To appreciate the challenge, consider the Earth's axial tilt changes slowly over time. The position of the sun on the horizon shifts throughout the year according to predictable astronomical cycles. Modern engineers use GPS receivers, satellite data, laser surveying equipment, and computer simulations to model these movements. The architects of Bryn Celli DDU relied solely on observation. Researchers still debate how they achieved such accuracy. Did they monitor solar positions over decades? Did they establish fixed observation points across the landscape? Was there a specialized class of prehistoric surveyors responsible for preserving astronomical knowledge? The mystery becomes even deeper when compared with other famous solar monuments. Sites such as Newgrange and Stonehenge display similar alignments, suggesting that communities separated by hundreds of kilometers may have shared sophisticated observational techniques. Yet, no written explanation survives. The monument still functions today. The knowledge that created it does not. Another mystery lies within the monument itself. Excavations uncovered a decorated stone engraved with spirals, curving lines, and geometric patterns. Similar symbols appear at several Neolithic sites across Britain and Ireland, but their meaning remains unknown. Creating such carvings required planning, consistency, and specialized tools. Archaeologists estimate that hundreds or even thousands of individual strikes may have been necessary to produce some designs. The patterns are not random scratches, they display deliberate organization and repeated motifs. Some researchers suggest they represent ceremonial symbolism. Others propose astronomical references or mnemonic systems used to preserve knowledge before writing existed. A few scholars have even speculated that they encoded information about seasons, rituals, or landscape features. Despite decades of study, no interpretation has achieved universal acceptance. Unlike Egyptian hieroglyphs or Mesopotamian cuneiform, there is no bilingual key that allows researchers to decode the symbols. The stone remains a message from a civilization that left no translation. Across Anglesey stand numerous megalithic monuments, including Barclodiad y Gowres and other stone tombs whose construction demanded extraordinary logistical capabilities. Many of the stones weigh several tons. Some may have been transported over distances of multiple kilometers. The challenge was immense. Experimental archaeology provides some clues. Modern teams attempting to recreate prehistoric transport methods have demonstrated that moving a 10-ton stone can require dozens or even hundreds of people using ropes, wooden rollers, sledges, and carefully prepared pathways. Yet the problem is not simply transportation. The builders also had to select appropriate stones, extract them from bedrock, shape them, coordinate labour, and place them with sufficient precision to ensure structural stability. Every stage required planning and organisation. This raises a difficult question. How were large engineering projects managed in societies without written contracts, formal engineering schools, or centralised bureaucracies? The monuments imply a level of social coordination far greater than traditionally imagined for Neolithic communities. Centuries after Bryn Celli DDU was constructed, Anglesey continued producing impressive engineering achievements. One of the most intriguing examples is Dinligwy, an ancient settlement dating largely to the Romano-British period. Its stone walls are extraordinarily thick. Some sections exceed 2 meters in width. Even more remarkable, they were built without mortar. The stability of these structures depends almost entirely on stone placement, weight distribution, and geometric locking. Modern structural engineers recognize similar principles in dry stone construction, but many details remain uncertain. Why have portions of these walls survived nearly 2,000 years of Welsh weather, while many later structures collapsed? What construction rules governed stone selection and placement? Were builders following standardized techniques passed down through generations? No manuals survive, only the stones remain. Anglesey also played an important role during the Bronze Age. Evidence from sites associated with copper extraction suggests that prehistoric communities possessed surprisingly advanced metallurgical expertise. Nearby mining regions, particularly around Paris Mountain, eventually became some of the richest copper-producing areas in Britain. Producing bronze required more than simply finding ore. Metal workers had to identify suitable deposits, construct furnaces, control airflow, maintain temperatures exceeding 1,000 degrees Celsius, and create molds capable of producing reliable tools and weapons. For comparison, many domestic fireplaces reach only a fraction of the temperatures needed for efficient metal smelting. Achieving such heat consistently demanded practical knowledge accumulated through generations of experimentation. Yet almost none of the technical instruction survived. Archaeologists can reconstruct furnaces and analyze slag residues. They can identify chemical compositions and production methods. But the decision-making processes behind those technologies remain largely invisible. The prehistoric hut circles on Holyhead Mountain reveal lost expertise in adapting to the environment. Despite Anglesea's strong winds, heavy rain, and changing weather, many were built in locations that balanced shelter, sunlight, water access, and nearby resources. Some settlements reduced winter heat loss and exposure to prevailing winds, while others used natural terrain for drainage and protection. Whether these solutions came from generations of experience or from a lost system of architectural knowledge remains unknown. What do you think is the greatest mystery of Anglesey? The solar alignment of Bryn Shelley DDU, the transport of massive stones, or the lost knowledge that disappeared with its builders? Tui Tonga was one of the most remarkable empires ever created without metal tools, wheeled transport, or written engineering manuals. Centered in the islands of Tonga in the South Pacific, this maritime kingdom controlled vast networks stretching across thousands of kilometers of ocean. Yet the greatest mystery is not how far the empire expanded. It is how a society that left behind almost no technical records achieved engineering, navigation, and shipbuilding feats that still challenge modern explanations. The story begins on the island of Tongatapu, the largest island of Tonga. Archaeological evidence suggests that the Tui Tonga dynasty emerged around the 10th century AD and gradually developed into the dominant political and ceremonial power across much of Western Polynesia. European explorers would not encounter the kingdom until centuries later. By then, the empire had already established influence over islands separated by distances that rival major continental trade routes. The discovery of monumental stone structures, royal tombs, and evidence of long-distance exchange reveal that ancient Tonga had achieved a level of organization far greater than previously imagined. The first great mystery involves the massive stone monuments associated with royal authority. The most famous example is Ha'amonga a Maui, often called the Stonehenge of the Pacific. The structure consists of 3 enormous limestone blocks forming a monumental gateway. The 2 vertical pillars weigh roughly 30 to 40 tons each, while the horizontal lintel is estimated at approximately 10 tons. Together they create a structure more than 5 meters high. What makes the monument extraordinary is not simply its size, but the technology required to construct it. Ancient Tonga possessed no iron tools, no cranes, no wheeled vehicles, and no draft animals. Yet builders quarried, transported, shaped, and elevated these enormous stones with remarkable precision. Modern engineers frequently compare the challenge to other megalithic construction projects around the world. While the blocks are smaller than some stones used at the Great Pyramid of Giza, they are comparable to many components of Stonehenge. Experimental archaeology demonstrates that moving stones weighing dozens of tons requires careful coordination, specialized knowledge, and significant labor. Yet no written explanation survives describing how the Tongans accomplished the task. Researchers continue debating whether ramps, timber rollers, earthen platforms, or other methods were employed. The monument stands as evidence of engineering knowledge that largely disappeared centuries ago. The second mystery centers on the royal tomb complexes known as langi. Scattered throughout the region of Lapaha are dozens of monumental tombs constructed from enormous limestone slabs. Some individual stones weigh more than 50 tons. The tombs consist of multiple, carefully arranged tiers that create impressive stepped platforms. Archaeologists have identified quarry sources several kilometers away, indicating that the stones were transported across challenging terrain before being assembled into highly organized structures. The engineering questions remain unresolved. How were these stones moved without metal machinery? How were upper layers precisely positioned? How was structural stability maintained over generations of construction? The scale becomes clearer through comparison. A modern family automobile typically weighs around 1.5 tons. Some stones used in the langi weigh the equivalent of more than 30 automobiles combined. Even with modern lifting equipment, moving such masses requires planning and expertise. The royal tombs suggest that Tonga possessed sophisticated construction techniques whose details have vanished from history. The third mystery concerns one of the largest oceanic political networks ever established before modern navigation. At its height, Tui Tonga maintained influence across a region extending from Tonga to Samoa, Fiji, Wallis, Futuna, and beyond. Some voyages involved distances exceeding 1,000 kilometers across open ocean. These journeys occurred centuries before the arrival of European navigational instruments. Today, ships rely on GPS satellites capable of determining location within meters. Ancient Polynesian navigators possessed none of these technologies. Instead, they mastered an extraordinary system based on stars, ocean swells, bird behavior, cloud formations, wind patterns, and environmental observations. Oceanographers studying traditional navigation have demonstrated that wave systems can travel thousands of kilometers across the Pacific, creating patterns detectable by experienced navigators. Skilled sailors learn to interpret these subtle signals as a form of natural map. Yet the full extent of this knowledge remains mysterious. Most of it was transmitted orally. Unlike the astronomical records preserved by ancient civilizations in Mesopotamia or Egypt, the navigational science of Tui Tonga was rarely written down. Modern researchers can reconstruct fragments of the system, but much of the original expertise disappeared before it could be fully documented. The fourth and perhaps greatest mystery involves shipbuilding without blueprints. Everything about the Tui Tonga Empire depended on ships. The movement of people, trade goods, tribute, political authority, and military power required vessels capable of crossing enormous distances. Historical accounts from European visitors describe massive Polynesian voyaging canoes that astonished foreign observers. Some double-hulled vessels exceeded 20 meters in length and could transport large numbers of passengers along with supplies necessary for long expeditions. The problem is that almost no technical plans survive. Modern shipbuilders depend on drawings, calculations, measurements, computer simulations, and engineering documentation. Every aspect of a vessel is carefully analysed before construction begins. Ancient Tonga appears to have achieved comparable practical results through entirely different means. Knowledge existed within communities rather than on paper. Researchers examining traditional Polynesian vessels have discovered evidence of remarkable hydrodynamic efficiency. Double-hulled designs provided stability in rough ocean conditions while minimizing drag. Flexible lashings connecting structural elements allowed vessels to absorb wave energy rather than resist it rigidly. In engineering terms, these ships behaved more like adaptive systems than fixed structures. What remains unexplained is how generations of builders optimized these designs without formal mathematics or written engineering manuals. How did they determine ideal hull proportions? How did they predict stability under varying loads? How did they select timber capable of surviving years of exposure to saltwater and storms? How did they transmit increasingly sophisticated design improvements across centuries without written records? Experimental reconstructions provide clues but not complete answers. In recent decades, replicas of traditional Polynesian voyaging canoes have successfully crossed thousands of kilometers of ocean. These voyages proved that ancient designs were capable of extraordinary performance. However, reconstructing a vessel from surviving traditions is not the same as understanding the entire developmental process that originally created the technology. Some maritime historians argue that Polynesian shipbuilding represented one of humanity's greatest engineering traditions. Unlike Mediterranean civilizations that developed ships in relatively enclosed seas, Polynesian builders designed vessels for the largest ocean on Earth. The Pacific covers approximately 165 million square kilometers, an area larger than all Earth's land masses combined. Successfully navigating and colonizing this environment required technological solutions of exceptional sophistication. The fifth mystery concerns administration without writing. Most major empires relied on written records to manage resources, tribute, diplomacy, and political authority. Ancient Egypt used hieroglyphic inscriptions. Imperial China maintained extensive bureaucratic archives. The Roman Empire generated enormous quantities of written documentation. Tui Tonga appears to have operated differently. The kingdom managed ceremonial relationships, tribute networks, and political obligations across multiple island groups, despite leaving behind very little written administration. Anthropologists believe that complex systems of oral tradition, genealogy, ritual authority, and collective memory played critical roles. Yet many details remain unclear. How were obligations tracked? How was information transmitted across vast distances? How was political continuity maintained over centuries? What do you think is the greatest mystery of the Tui Tonga Empire? The transport of massive stone monuments, the lost art of Pacific navigation, or the shipbuilding knowledge that crossed an ocean without leaving behind a single blueprint? Share your thoughts in the comments below. Traprain Law is a volcanic hill rising above the landscape of East Lothian, Scotland. For centuries, this rocky summit dominated the surrounding countryside. What appears today as a lonely hill once hosted one of the largest and most powerful settlements in northern Britain. Yet the greatest mystery of Traprain Law is not its walls, its treasures, or even its rulers. It is the evidence that this remote hilltop functioned as a major industrial centre, capable of large-scale metal production centuries before advanced machinery, modern surveying, or written engineering manuals existed. The story of Traprain Law began long before archaeologists understood its significance. Antiquarians recognized the hill's unusual shape during the 19th century, but systematic excavations did not begin until the early 20th century. Between 1914 and 1923, extensive investigations led by archaeologist Alexander Curl revealed an astonishing quantity of artifacts. Beneath the grass-covered summit were the remains of a vast Iron Age settlement occupied for more than 1,000 years. Excavators uncovered houses, defensive structures, workshops, imported goods, and evidence of industrial activity on a scale that few researchers expected to find so far beyond the Roman frontier. One of the first mysteries concerns the sheer size of the settlement itself. During its peak, Traprain Law enclosed approximately 16 hectares of defended space, making it one of the largest known hill forts in Scotland. To understand the scale, the enclosed area was larger than many contemporary settlements elsewhere in northern Britain. Archaeological evidence suggests that hundreds, perhaps thousands of people may have occupied the site at different periods. Such a population raises difficult questions. How was food transported to the summit? How was water supplied throughout the year? How were building materials moved onto steep volcanic slopes? Modern researchers can identify structures and storage areas, but the complete logistical system remains unknown. The challenge becomes even more impressive when compared with other elevated settlements. Like Machu Picchu in Peru, Traprain Law required sustained management of resources in a location that was naturally difficult to access. Yet, unlike Machu Picchu, almost no written records survive to explain how the system operated. The hill's defences present another technological mystery. Excavations revealed multiple phases of fortification stretching across centuries, and massive stone ramparts and earthworks transformed the volcanic summit into a formidable stronghold. Constructing such defences required more than physical labour. Builders had to understand terrain, structural stability, drainage, and strategic positioning. The volcanic slopes contain uneven surfaces, exposed rock formations, and difficult gradients. Despite these challenges, the defensive lines followed routes that maximized visibility and protection. Modern military engineers recognized the importance of elevation in defensive planning. Traprain law provided views across vast portions of southeastern Scotland, allowing observers to monitor movement for many kilometres. Yet researchers still debate how Iron Age builders determined the optimal placement of walls without advanced surveying equipment. The problem becomes even more fascinating when considering the volume of material involved. Thousands of tons of stone had to be extracted, transported, and assembled, and the organisational knowledge required for such a project remains largely invisible in the archaeological record. The most extraordinary mystery at Traprain Law involves metallurgy. Archaeologists uncovered substantial quantities of ironworking debris, including slag, furnace remains, metalworking waste, and evidence of smithing activity. These discoveries indicate that Traprain Law was not merely a political centre, it was also a manufacturing centre. This conclusion creates a technological puzzle. Iron production is one of the most demanding industries of the ancient world. Unlike bronze, iron requires significantly higher temperatures. Experimental archaeology demonstrates that bloomery furnaces typically needed temperatures exceeding 1,100 degrees Celsius to reduce iron ore into usable metal. Maintaining such temperatures without modern fuel systems, thermometers, or controlled airflow is an enormous challenge. Yet the inhabitants of Traprain Law appear to have achieved this repeatedly. Researchers have identified large quantities of slag, the glass-like waste produced during smelting. Slag is often described as the fingerprint of ancient metallurgy, because its volume can reveal the scale of production. At Traprain Law, the quantity suggests sustained industrial activity rather than occasional metalworking. The mystery deepens when considering fuel consumption. Producing iron required vast amounts of charcoal. Modern estimates from experimental bloomery reconstructions suggest that several kilograms of charcoal might be necessary to produce a single kilogram of workable iron. This implies a sophisticated supply network extending far beyond the hill fort itself. Where did the ore originate? How was charcoal production organised? How did smiths regulate furnace temperatures? How did they maintain consistent quality across generations? No written manual survives to answer these questions. Even more intriguing is the possibility that Traprain Law functioned as a regional manufacturing hub. Iron tools, weapons, agricultural equipment, and trade goods may have been produced here and distributed across large portions of southeastern Scotland. If true, the settlement operated less like a simple tribal fortress and more like a specialised industrial centre. The comparison with other ancient production sites is striking. Roman iron complexes in Britain, such as those in the Weald, are famous for large-scale output. Yet Traprain Law existed beyond direct Roman administration. The technological expertise displayed here suggests that local communities possessed metallurgical knowledge that rivaled some contemporary centres within the Roman world. The greatest mystery is that the technical knowledge behind this industry vanished. The slag survived, the furnaces survived, the tools survived, but the methods disappeared. Although Traprain Law stood beyond the permanent northern frontier of the Roman Empire, Roman influence is visible throughout the archaeological record. Excavators discovered imported goods, Roman objects, and evidence of extensive contact with Imperial Britain. These discoveries challenge the traditional image of a sharp boundary separating Rome from the peoples beyond its frontier. Instead, the evidence suggests a complex network of trade, diplomacy, and economic exchange. The hill fort occupied a strategic position between Roman-controlled territories and the independent communities farther north. Some historians believe the local Votadini tribe benefited from this position, acting as intermediaries in the regional commerce. Yet many questions remain unresolved. Were Roman goods acquired through trade, diplomatic gifts, military alliances, or payments? Did local elites cooperate with Rome, resist Rome, or alternate between both strategies? The archaeological evidence supports multiple interpretations, but provides no definitive answer. In 1919, excavators made one of the most important discoveries in Scottish archaeology, the Traprain treasure. The hoard contained more than 24 kilograms of Roman silver. Plates, vessels, and luxury objects had been cut into fragments before burial. Today it remains one of the largest Roman silver hoards ever discovered outside the empire's core territories. The treasure raises profound questions. Why was such an enormous quantity of silver located beyond Rome's frontier? Why were valuable objects deliberately cut into pieces? Why was the hoard buried and never recovered? Some scholars suggest diplomatic payments. Others propose military subsidies, trade transactions, or accumulated wealth belonging to local rulers. The fragmentation of the silver is particularly puzzling. Many experts believe the pieces functioned as bullion valued by weight rather than appearance. If correct, the treasure represents evidence of a sophisticated economic system operating far beyond the imperial frontier, yet certainty remains elusive. For centuries, Traprain law was one of the most influential centres in northern Britain. Then it declined. The process appears gradual rather than catastrophic. Archaeologists have found no evidence of a single devastating attack or natural disaster that explains the abandonment. Instead, the decline may reflect larger transformations occurring across Britain during the late Roman and post-Roman periods. Trade routes shifted, political alliances changed, new centres of power emerged, but no single explanation fully accounts for the disappearance. The settlement that once controlled trade networks, managed industrial production, and accumulated immense wealth eventually lost its prominence. Like many ancient centres of power, it faded while leaving behind only fragments of its story. Which mystery of Traprain law fascinates you the most? Let us know your thoughts in the comments below. Hoa Lu ancient capital is located in Ninh Binh province, northern Vietnam. More than 1,000 years ago, its builders transformed a landscape of limestone mountains, rivers, marshes, and narrow valleys into one of the most formidable capitals in Southeast Asia. The palaces vanished, the wooden structures disappeared, yet the earth walls remain. Some still rise across the valleys after a millennium of monsoon rains, floods, erosion, and human activity. Modern archaeologists can map the terrain with satellites and drones, but one question remains unresolved. How did 10th century engineers create a defensive system so perfectly integrated with nature that parts of it continue functioning today? Hoa Lu was known through historical records from the Dinh and early Le dynasties, but systematic archaeological investigations expanded significantly during the 20th and 21st centuries. Excavations revealed palace foundations, ancient bricks, ceramics, defensive structures, waterways, and extensive earthworks hidden beneath the modern landscape. Most ancient capitals were built by constructing walls around cities, but Hoa Lu followed a different principle. Instead of forcing the landscape to adapt to the city adapted to the landscape. The ancient capital occupied an area surrounded by towering limestone karst mountains, some rising more than 200 meters above the surrounding valleys, creating a natural fortress unlike anything else in Vietnam. Geological studies show that the karst system developed over millions of years through the dissolution of limestone by water, and by the 10th century the region already consisted of hundreds of steep peaks separated by narrow corridors. The mystery is how engineers surveyed and organized such a complex environment without modern mapping technology. Today, military planners use aerial photography, LiDAR scanning, GPS systems, and digital terrain models to identify strategic choke points. The builders of Hoalu had none of these tools, yet they selected locations where narrow valleys could be sealed with relatively short sections of artificial walls, while the surrounding mountains acted as enormous natural barriers. Researchers comparing the site with famous fortified landscapes such as Machu Picchu and Masada have noted similar principles. Geography itself became architecture. The result was extraordinary. Instead of defending hundreds of hectares with continuous walls, Hoalu's builders used mountains as ready-made fortifications, dramatically reducing construction requirements while increasing defensive strength. The calculations behind that decision remain largely invisible. The most fascinating technological mystery of Hoalu is not its temples or palaces, but its enormous earth walls. Historical records and archaeological surveys indicate that sections of the defensive system stretched across valleys connecting limestone mountains. In some locations, the walls originally stood approximately 8 to 10 meters high and were tens of meters thick at the base. Building such structures today would require geotechnical studies, soil analysis, compaction testing, and erosion control engineering, yet Hoalu's builders achieved remarkable durability more than 1,000 years ago. This creates a major archaeological puzzle. Northern Vietnam experiences a humid subtropical climate, and average annual rainfall in Ninh Binh often exceeds 1,800 millimeters. Monsoon storms repeatedly saturate the soil while seasonal flooding affects surrounding river systems. Under such conditions, earth structures normally degrade rapidly unless carefully engineered. Yet significant portions of Hoalu's earthwork survived for over a millennium. Excavations suggest that the walls were not simple piles of dirt. Researchers have identified evidence of layered construction techniques. Different soil types may have been selected and compacted in stages, while some sections appear denser than others, indicating deliberate engineering rather than random accumulation. The challenge is that the original construction manuals do not exist. Modern engineers understand that soil stability depends on moisture content, grain size distribution, compaction pressure, slope geometry, and drainage characteristics. Even small mistakes can cause collapse. Ancient builders somehow managed these variables without laboratory equipment. Comparisons can be made with the massive earthworks of Cahokia, where Monk's Mound contains an estimated 622,000 cubic meters of earth, and with Poverty Point, where monumental earthen ridges survived for thousands of years. In each case, archaeologists continue debating the precise engineering methods used. Hoalu belongs to the same category of mystery. One particularly intriguing question concerns drainage. Modern embankments often fail because water accumulates inside the structure. Some researchers suspect Hoalu's walls incorporated sophisticated drainage strategies, but direct evidence remains limited. If true, the builders may have possessed practical geotechnical knowledge far beyond what surviving historical texts reveal. Even after centuries of weathering, parts of the system still demonstrate an engineering success that modern science cannot fully reconstruct. The earth walls were only part of the defensive system. Water played an equally important role. Hoalu stood near the Huawang Long River and a network of natural waterways connecting the Red River Delta. Archaeological and geographical studies suggest that rivers, marshes, and flooded lowlands formed additional defensive barriers. The unanswered question is how much of this network was natural and how much was modified by human intervention. Ancient engineers around the world frequently reshaped water systems for defense. The inhabitants of Angkor constructed vast hydraulic networks. Medieval Dutch communities engineered defensive flooding systems, and Chinese dynasties diverted rivers around fortified cities. Did Hualu's rulers employ similar strategies? Some historians suspect canals and water control features may have enhanced mobility while restricting enemy movement, while others argue the natural landscape alone provided sufficient protection. Without complete archaeological evidence, the true scale of hydraulic engineering remains uncertain. Building a capital inside a karst labyrinth required more than engineering. It required logistics. The transportation challenge was enormous. Millions of kilograms of soil had to be moved. Timber was needed for palaces and defensive structures. Stone had to be quarried and transported, and food had to support laborers throughout construction. Today, heavy machinery performs such tasks efficiently, but 10th century builders relied entirely on human labor, animals, boats, and simple tools. Researchers still debate how construction materials move through the mountainous terrain. Water transport may have been the key. A single river barge can move loads equivalent to dozens of carts, and some scholars believe waterways functioned as ancient highways supplying the growing capital. Yet no complete reconstruction of the transportation network currently exists. The operational system behind the construction effort remains largely hidden. The structures most people imagine when thinking about a capital are precisely the structures that disappeared. Wood dominated elite architecture in ancient Vietnam. Unlike stone monuments that survive for millennia, timber buildings decay rapidly in tropical climates. Excavations have uncovered foundations, column bases, decorative materials, roof tiles, bricks, and ceramics. These remains confirm the existence of sophisticated palace complexes. The problem is scale. How large were they? Some foundations suggest substantial ceremonial buildings, while decorative architectural elements indicate advanced craftsmanship. Yet archaeologists possess only fragments of the original picture. This creates a situation similar to other vanished capitals throughout Asia, where surviving foundations hint at grandeur far exceeding what remains visible today. The true appearance of Hualu's royal center remains one of Vietnam's most intriguing historical puzzles. What do you think is the greatest mystery of Hualu ancient capital? The giant earth walls, the hidden water defenses, or the lost engineering knowledge behind the entire fortress system? Located on Inishmore, the largest of Ireland's Aran Islands, at the edge of a 100-metre-high Atlantic cliff, Dunangassa was first scientifically documented during the 19th century and extensively excavated between 1992 and 1995 under archaeologist George Eogan. Radiocarbon evidence suggests that the earliest construction began around 1100–900 BC, with major expansions continuing through the Iron Age. More than 3,000 years later, the site remains one of archaeology's most puzzling engineering mysteries. What makes the site remarkable is not merely its age, it is the combination of location, scale, defensive complexity, and technical sophistication. Even with modern archaeological methods, researchers still debate why it was built, how its builders organized such an enormous project, and whether the monument visible today represents only a fraction of the original structure. The first mystery begins with the location itself. Dunangassa occupies one of the most dramatic positions of any prehistoric fortification in Europe. The monument stands directly beside a vertical limestone cliff overlooking the Atlantic Ocean. Today, visitors see the fort ending abruptly at the cliff edge, creating the impression that the builders intentionally used the sea as part of the defense system. However, geological evidence suggests a more complicated story. The Aran Islands are continuously shaped by Atlantic erosion. Storm waves, salt weathering, and cliff collapse have altered the coastline for thousands of years. Many researchers suspect that a significant portion of Dunangassa may have disappeared into the ocean. If true, the monument visible today could represent only part of a much larger complex. This possibility creates an important engineering question. If substantial sections have been lost, how large was the original structure? And how did prehistoric builders design a monument beside an unstable coastal environment without the surveying tools available today? Modern engineers use satellite imagery, digital terrain models, and geological mapping to evaluate cliff stability. The builders of Dunangassa relied entirely on observation and accumulated knowledge. Yet the surviving sections remain standing after more than 3 millennia of exposure to Atlantic storms. The second mystery involves the enormous scale of construction. The fort consists of multiple concentric defensive walls surrounding a central enclosure approximately 50 meters in diameter. The outer defenses extend across a much larger area. Thousands of limestone blocks were transported, positioned, and assembled into dry stone walls without mortar. Unlike later medieval castles, these walls depend entirely on gravity, friction, and careful stone placement. Experimental archaeology demonstrates that dry stone construction requires a detailed understanding of load distribution. Individual stones must interlock in ways that prevent movement while allowing the structure to absorb environmental stress. A poorly built wall can collapse within decades. Dunangassa has survived for more than 3,000 years. The engineering challenge becomes even more impressive when compared with other prehistoric sites. The famous hill forts of Britain often relied heavily on earthworks and timber. Dunangassa instead used massive quantities of stone in an environment where transportation was exceptionally difficult. Researchers still cannot determine exactly how labour was organised. Moving thousands of tons of limestone across a rocky island landscape would have required planning, coordination, and manpower on a scale rarely associated with Bronze Age communities. The third mystery is perhaps the most famous feature of the site. Outside the main walls lies a vast field of upright limestone slabs known as a chevaux de frise. More than 2,500 to 3,000 stone pillars protrude from the ground at irregular angles. Covering a substantial area in front of the fort, they create what appears to be a prehistoric obstacle course. Archaeologists generally interpret the feature as a defensive system designed to slow attackers, yet significant questions remain. No other known prehistoric fortification in Europe contains a chevaux de frise of comparable scale and preservation. Researchers continue debating its actual effectiveness. Would attackers simply move around it? Was it intended to stop infantry carrying shields? Could it have been designed to obstruct livestock raids rather than military assaults? Some scholars have proposed an alternative possibility. The structure may have possessed symbolic or ceremonial significance in addition to any defensive role. The immense labour required to install thousands of stone slabs would have communicated power and authority to anyone approaching the site. This interpretation finds parallels elsewhere in archaeology. Monuments such as Stonehenge, the Karnak alignments in France, and certain Scandinavian stone settings combined practical and symbolic functions. Dunangassa may belong to the same category. The fourth mystery concerns geometry and planning. The fort did not emerge during a single construction phase. Excavations indicate multiple stages of expansion spanning centuries. This raises a remarkable question. How did successive generations maintain coherent architectural design across such long periods? Today, engineers use standardized measurements, written plans, and mathematical calculations. The builders of Dunangassa possessed none of these tools in modern sense, yet the monument displays clear evidence of organized planning. Archaeologists studying prehistoric construction often encounter this problem. Sites appear more geometrically sophisticated than expected, based on surviving evidence of technology. Similar debates surround Iron Age hill forts in Britain, neuralgic structures in Sardinia, and certain Celtic oppida across continental Europe. Dun Angasa contributes to this broader mystery of lost engineering knowledge. The fifth mystery involves the purpose of the monument itself. At first glance, the answer appears obvious. Massive walls suggest a fortress. Yet the archaeological evidence complicates this interpretation. Excavations recovered pottery, tools, animal remains, and evidence of human activity. However, the quantity of domestic material is relatively limited compared with what might be expected from a permanently occupied settlement. If the site functioned primarily as a military stronghold, why invest enormous resources on an isolated Atlantic island? If it served as an elite residence, why choose such a remote and exposed location? If it was a ceremonial centre, why surround it with extensive defensive architecture? Several competing theories exist. Some researchers argue that Dun Angasa served as a regional centre of power controlling maritime routes through Galway Bay and the Atlantic coast. Others view it as a refuge used during periods of conflict. Another interpretation suggests that ritual activity and political authority may have been inseparable, making the monument simultaneously a ceremonial and defensive space. No explanation fully resolves all available evidence. The sixth mystery concerns environmental knowledge. The Aran Islands experience some of the harshest weather conditions in Ireland. Atlantic storms generate powerful winds and heavy salt exposure. Modern coastal engineers study such environments using computer simulations and climate models. The builders of Dun Angasa possessed neither, yet they selected a location where the underlying limestone bedrock provided exceptional stability. They created walls capable of resisting centuries of environmental stress. They designed a monument that remains visible despite continuous exposure to one of Europe's most energetic coastal environments. This suggests a practical understanding of geology and landscape behaviour far more advanced than commonly assumed. Taputapuatea Marae, on the island of Raiatea in French Polynesia, was not a fortress, a palace, or a city. Yet it may have controlled the largest navigation network ever created without maps, compasses, metal instruments, or writing. From this sacred complex, Polynesian navigators crossed an ocean covering nearly 30 million square kilometers, an area larger than Africa, using knowledge that modern science still struggles to fully explain. European explorers recorded the site during the 18th century, but its true significance emerged through archaeological investigations conducted throughout the 20th century. Excavations reveal that Taputapuatea was far more than a ceremonial centre. It was the intellectual heart of a civilization that connected thousands of islands across the Pacific long before modern navigation existed. The greatest mystery surrounding Taputapuatea is not its stone structures, but the extraordinary navigation system associated with it. Archaeological, linguistic, and genetic evidence demonstrates that Polynesian voyagers successfully settled one of the largest regions ever explored by a pre-industrial civilization. Their voyages stretch from Tonga and Samoa to Hawaii in the north, New Zealand in the south, and Easter Island in the east. The resulting Polynesian triangle covers approximately 25 to 30 million square kilometers of ocean. To appreciate the scale of this achievement, consider that the distance between Tahiti and Hawaii exceeds 4,000 kilometers, while Tahiti to New Zealand is roughly the same. These journeys were conducted in wooden double-hulled canoes without magnetic compasses, sextants, chronometers, charts, or written instructions. Modern navigation relies heavily on GPS satellites orbiting approximately 20,000 kilometers above Earth. Polynesian navigators possessed none of these technologies, yet they repeatedly located tiny islands scattered across the largest ocean on the planet. Researchers have spent decades attempting to understand how this was possible. Experimental voyages conducted by the Polynesian Voyaging Society demonstrated that traditional navigation methods could indeed work. The famous canoe Hokulea successfully sailed thousands of kilometers using traditional techniques. However, proving that navigation was possible does not fully explain how knowledge was transmitted across generations with such precision. Traditional accounts describe navigators memorizing hundreds of stars, seasonal wind patterns, ocean swells, bird migrations, cloud formations, and wave reflections. Some scholars estimate that master navigators possessed information equivalent to entire libraries stored only in human memory. The most astonishing aspect is accuracy. Many Pacific islands are extremely small targets, with some rising only a few square kilometers above sea level. Missing an island by even a few degrees could result in hundreds of kilometers of error and certain failure. Yet Polynesian settlement expanded successfully for centuries. Scientists today can model wave patterns using satellites and supercomputers. Even so, the full cognitive system used by ancient navigators remains only partially understood. The knowledge network centered on Taputapuatea may represent one of the most sophisticated non-written technologies ever developed. Taputapuatea appears to have functioned as more than a religious site. Oral traditions describe it as a gathering place where priests, chiefs, and navigators from distant islands exchanged knowledge. This raises a remarkable question. How did a civilization without writing maintain consistency across an ocean larger than the continental United States? In literate societies, technical knowledge survives through documents. Roman engineers left architectural manuals, medieval sailors created charts, and Chinese dynasties recorded astronomical observations. Polynesian civilization relied primarily on oral transmission. The challenge is enormous because studies of human memory show that information naturally changes as it passes between generations. Yet many Polynesian traditions remained recognizable across thousands of kilometers of ocean. Some researchers compare Taputapuatea to an ancient university, while others describe it as a navigation academy. Neither description fully captures its role, but both emphasize its apparent importance as a center of knowledge preservation. The mystery is not merely what people learned there. The mystery is how that knowledge remained accurate for centuries without written records. At first glance, Taputapuatea may appear simple compared to the pyramids of Egypt or the monumental architecture of Rome. However, the construction itself raises important technical questions. The complex contains carefully arranged basalt and coral limestone structures, with some stones weighing several tons. Raiatea is a volcanic island characterized by steep terrain, dense vegetation, and challenging transportation conditions. Archaeologists still debate the logistics involved in quarrying, moving, and positioning these stones. Unlike civilizations equipped with wheeled transport or draft animals, Polynesian builders relied entirely on human labor and traditional engineering methods. The challenge becomes even more impressive when considering environmental conditions. French Polynesia experiences heavy rainfall, tropical storms, humidity, and long-term erosion, yet portions of the site have survived for centuries. Researchers continue investigating how builders selected foundation locations, managed drainage, and stabilized structures using locally available materials. While the scale is smaller than sites such as Giza, the environmental engineering challenges were significant. Taputapuatea's influence extended far beyond Raiatea itself. Archaeological comparisons reveal similarities between ceremonial structures found across numerous Polynesian islands. Related traditions appear in Hawaii, the the Cook Islands, the Marquesas, New Zealand, and other island groups separated by thousands of kilometres. This creates another unresolved question. How was cultural coordination maintained across such immense distances? For comparison, the Roman Empire relied on roads extending roughly 400,000 kilometres. The Polynesians possessed no roads at all. Their transportation network consisted entirely of open ocean. Yet architectural concepts, religious practices, and social structures spread across vast regions with remarkable consistency. Some scholars argue that regular long-distance voyages maintained communication, while others suggest that knowledge moved through periodic ceremonial gatherings linked to centres such as Taputa Puatea. Neither explanation completely accounts for the extraordinary level of cultural connectivity observed throughout Polynesia. One of the least appreciated mysteries involves environmental observation. Ancient Polynesian navigators transformed natural phenomena into navigational instruments. Ocean swells became directional indicators, birds became biological tracking systems, and clouds functioned as distant markers of land. Modern meteorology uses satellites capable of observing entire weather systems from space, whereas Polynesian navigators relied entirely on direct observation. Recent scientific studies have confirmed that some traditional methods possess genuine physical foundations. Islands can alter wave behavior, certain bird species follow predictable flight patterns, and clouds often form differently above land masses. However, researchers remain amazed by the level of expertise required to integrate all these variables simultaneously. A navigator crossing thousands of kilometers of open ocean had to process information continuously while adapting to changing weather conditions. In many respects, this resembles a biological navigation computer operating entirely within the human brain. Exactly how navigators acquired and maintained such expertise remains unclear. What do you think was the real secret behind the navigators of Taputa Puatea? Was it an extraordinary system of observation, a lost method of training, or a form of knowledge that modern science still does not fully understand? Share your thoughts in the comments below. Twin Gare is an Iron Age hill fort overlooking the Usk Valley in southeastern Wales. More than 2,000 years ago, long before maps, satellites, aerial photography, or modern surveying instruments existed, its builders selected one of the most strategically effective positions in the region. Today, archaeologists can analyze the landscape using LiDAR scans, GIS software, and digital elevation models. Yet one of the greatest mysteries remains how Iron Age communities identified such locations with remarkable precision, using only the knowledge available to them at the time. The site was recognized by antiquarians centuries ago and later examined through archaeological surveys of Welsh hill forts. Although Twin Gare has never received the same level of excavation as famous sites such as Maiden Castle or Danebury, modern landscape studies have revealed that its position was far from accidental. The hill fort occupies a commanding ridge above important natural movement corridors through the Usk Valley, one of the principal routes connecting the interior of Wales with surrounding regions. The greatest mystery surrounding Twin Gare is not its walls, its ditches, or even its age. It is how its builders surveyed an entire mountain landscape without any known surveying technology. Today, determining the best defensive location requires sophisticated tools. Military planners use satellite imagery, topographic mapping, GPS systems, and computer-generated visibility analyses. Archaeologists studying hill forts often use GIS software capable of calculating viewsheds, the areas visible from a specific location. Such analyses frequently reveal that Iron Age forts occupy positions with extraordinary control over surrounding terrain. Twin Gare is one of those locations. From its elevated position, large portions of the Usk Valley can be observed. Routes approaching from different directions become visible long before travellers arrive. The fortress effectively functions as a natural observation platform. Yet selecting such a position would have required understanding the landscape on a regional scale. The builders would have needed to know not only where they stood, but also how that location related to dozens of surrounding hills, ridges, valleys, and pathways. This creates a fascinating technological puzzle. How did Iron Age communities map terrain without maps? How did they evaluate visibility across tens of kilometers? How did they identify optimal positions among countless possible hilltops? Some researchers suggest that generations of accumulated local knowledge may have functioned as a form of practical surveying. Communities moving livestock, trading goods, and travelling across the region would have developed intimate familiarity with the landscape. Over centuries, this knowledge could have become detailed enough to guide large-scale construction projects. Even so, the precision remains impressive. Modern computer analyses often confirm that these ancient choices were remarkably effective. The second mystery involves the engineering required to transform a hilltop into a fortress. At first glance, earthwork defences may appear simple compared to Roman aqueducts or Egyptian pyramids. In reality, moving enormous quantities of soil without machinery represents a major engineering challenge. The defensive system at Twini Gare consists of banks and ditches constructed entirely through manual labour. Every cubic metre of earth had to be excavated, transported, and compacted by human effort. Experimental archaeology has demonstrated that prehistoric communities using basic tools can move substantial volumes of soil, but doing so requires careful organisation and planning. The challenge becomes even greater when considering scale. Studies of large British hill forts suggest that some defensive systems required tens of thousands of labour days. Even smaller hill forts demanded coordinated workforces capable of sustaining construction over extended periods. The builders of Twini Gare not only moved vast quantities of material, but also shaped earthworks that have survived more than 2 millennia of erosion. This raises questions that remain unanswered. Who designed the defences? How are construction crews organised? How are measurements maintained across irregular terrain? No written plans survive. No engineering manuals exist. The physical remains suggest knowledge, but the methods have disappeared. The third mystery concerns the geometry of defence. Many Iron Age hill forts in Britain employ sophisticated arrangements of ditches, ramparts, entrances and natural obstacles. Twini Gare appears to have been carefully integrated into the surrounding landscape, rather than simply placed upon it. Modern military engineers understand the importance of controlling movement. Defensive systems are often designed to funnel attackers into predictable routes while maximising visibility for defenders. Similar principles seem visible in numerous Iron Age forts. At Twini Gare, the terrain itself became part of the fortification system. Steep slopes reduced vulnerability, natural contours strengthened defences, and artificial earthworks enhanced existing advantages. The result resembles a form of landscape engineering. Instead of imposing a fortress upon nature, the builders modified nature itself into a defensive machine. Whether this knowledge emerged through trial and error or represented a sophisticated tradition passed across generations remains unknown. The fourth mystery involves communication. Twini Gare did not exist in isolation. Across Wales and Britain, hundreds of hill forts occupied elevated positions. Some appear capable of maintaining direct lines of sight with neighbouring high points. This has led some researchers to consider whether certain hill forts formed communication networks. The concept is not unprecedented. The Roman Empire used beacon systems to transmit warnings across long distances. Medieval kingdoms later employed similar techniques. Even ancient China developed signal tower networks stretching across vast territories. Could Iron Age Britain have possessed a simpler version of the same concept? No direct evidence has been discovered at Twin Gare. No preserved beacon structures survive, yet the strategic placement of many hill forts continues to fuel debate. If visual communication existed, information could potentially travel across large regions far faster than a messenger traveling on foot. The possibility remains one of the most intriguing unresolved questions in British archaeology. The fifth mystery is environmental engineering. Twin Gare has survived more than 2,000 years. Throughout that period, the site experienced heavy rainfall, winter storms, seasonal freeze-thaw cycles, soil movement, vegetation growth, and continuous erosion. Yet significant portions of the earthworks remain visible today. This durability suggests practical knowledge of slope stability and drainage. Modern geotechnical engineers understand that improperly constructed earthworks can fail within years or decades. Water infiltration weakens structures. Erosion gradually destroys embankments. Poor drainage accelerates collapse. The builders of Twin Gare clearly lacked modern engineering equations, but they may have possessed something equally valuable: centuries of accumulated experience. By observing which embankments survived and which failed, generations of builders could gradually refine construction methods. The resulting knowledge may have been transmitted orally rather than through written records. If so, an entire engineering tradition vanished without leaving documentation. The sixth mystery concerns what is missing. The hill foot visible today is almost certainly incomplete. Archaeologists primarily see the earthworks because soil survives while wood decays. Any timber palisades, towers, gates, platforms, storage buildings, workshops, or dwellings that once occupied the site have largely disappeared. This creates a distorted picture of the original fortress. Imagine future archaeologists studying a modern city after all steel, glass, concrete and plastic had vanished. Only foundations would remain. Much of the complexity would be invisible. The same problem exists at Twin Gare. What survives may represent only the skeleton of a far more sophisticated settlement. Recent technologies such as LiDAR have transformed archaeological investigation by revealing subtle landscape features hidden beneath vegetation. Similar surveys elsewhere in Britain have uncovered previously unknown structures, pathways, and earthworks. As these methods continue advancing, researchers may discover that Twin Gare was more complex than currently understood. What do you think was the greatest achievement of Twin Gare's builders? Surveying an entire mountain landscape, constructing massive defences by hand, or the lost knowledge behind it all? Share your thoughts in the comments below. Dunakire is a tiny sea-stack fortress rising from the North Sea coast of Aberdeenshire, Scotland. Perched on an isolated rock surrounded by crashing waves, it preserves one of the most puzzling engineering mysteries of the ancient Picts. Long before medieval castles dominated Scotland, someone managed to build defensive structures on a narrow pillar of rock that remains difficult to access even with modern climbing equipment. The greatest question is simple. How did ancient builders construct and maintain a fortress in a place that seems almost impossible to reach? Discovery of Dunakire was surprisingly recent. Antiquarians recorded carved Pictish symbol stones near the site during the 19th century, but systematic archaeological investigations only intensified in the 21st century. Excavations and surveys revealed remnants of defensive walls, timber structures and occupation layers dating roughly between the 2nd and 4th centuries AD. These findings potentially make Dunakire one of the earliest known Pictish fortified sites ever identified. The first mystery begins with geography itself. Dunakire sits atop a sea stack approximately 20 meters above the water. Today, reaching the summit requires technical climbing and careful navigation along dangerous coastal cliffs, and archaeologists have described access conditions as extremely challenging even with modern safety equipment. Yet evidence suggests that ancient inhabitants transported construction materials, timber, food supplies, and daily necessities onto this isolated rock. Stone ramparts once enclosed much of the summit, wooden structures stood within the defensive perimeter, and human occupation continued long enough to leave substantial archaeological deposits. The engineering challenge becomes clearer when compared to other ancient fortifications. The famous hill fort of Maiden Castle in England occupies more than 19 hectares of land and offers broad access routes for labour and construction. Dunkerque, by contrast, occupies only a tiny fraction of that area and stands separated from the mainland by sheer cliffs and rough seas. Every stone used in construction had to be carried upward, every timber beam had to reach the summit, and every person who lived there had to climb to the top. Unlike large inland settlements, Dunkerque offered almost no room for error, and one accident could send workers falling directly into the North Sea below. Researchers still debate whether the sea stack was more accessible during antiquity. Geological evidence suggests coastal erosion has significantly altered the landscape over the last 2 millennia. Some scholars propose that Dunkerque may once have been connected to a narrow ridge or partially attached headland. If true, much of the original access route has disappeared. However, no definitive reconstruction exists, leaving one of the site's most important engineering questions unanswered. Among all mysteries surrounding Dunkerque, none is more intriguing than the apparent ability of its builders to construct on terrain constantly attacked by the sea. The North Sea is one of the most energetic marine environments in Europe. Winter storms regularly generate waves exceeding several meters in height. Strong winds accelerate erosion along exposed coastlines. Salt water penetrates cracks in stone, and repeated freezing and thawing cycles widen fractures over time. Modern coastal engineers spend billions of dollars annually protecting infrastructure from these forces. Ancient builders at Dunkerque face the same environmental threats without concrete steel reinforcement, satellite monitoring, computer modelling, or modern geology. Yet archaeological remains indicate that defensive structures survived long enough to serve their intended purpose. This raises a remarkable question. How much did the Picts understand about coastal erosion? Modern geological studies show that wave energy concentrates on exposed headlands and isolated rock formations. Sea stacks typically experience some of the highest erosion rates along a coastline because they are attacked from multiple directions. Selecting such a location for construction appears counterintuitive. However, the builders may have recognized something important about the local geology. Dunkerque is composed of hard, sedimentary rock capable of resisting erosion more effectively than surrounding formations. Without formal geological science, ancient engineers may have identified stable rock through observation accumulated over generations. This pattern appears elsewhere in history. Builders of Machu Picchu selected bedrock foundations resistant to landslides, while Roman engineers often positioned harbours where natural geological features minimized wave damage. The creators of Dunkerque may have possessed a similarly sophisticated understanding of their environment. The mystery deepens when examining the surviving defensive walls. Even though much of the original structure has vanished, the placement of remaining masonry suggests builders deliberately positioned fortifications where the underlying rock provided maximum stability. Such decisions imply planning rather than improvisation. No written records explain how these choices were made. The Picts left no engineering manuals, no construction instructions, and no technical diagrams. Their knowledge survives only through the physical evidence itself. Perhaps most astonishing is the possibility that the sea stack visible today is only a fragment of the original landscape. If erosion removed sections of the ancient approach route, then the surviving fortress represents a structure designed not merely to withstand decades of storms but centuries of geological change. Modern researchers can estimate erosion rates using drones, laser scanning, and computer simulations. Ancient builders relied entirely on experience. The fact that they successfully established a functioning fortress in such a hostile environment remains one of the strongest indicators of sophisticated environmental knowledge in early Pictish society. Even if construction was possible, survival presents another puzzle. A sea stack offers almost no natural resources. Fresh water is limited, agricultural production is impossible, and space for storage is extremely restricted. Archaeological evidence indicates that people nevertheless occupied Dunakaya for extended periods, implying the existence of a reliable supply network connecting the fortress with settlements on the mainland. The logistical challenge resembles that faced by isolated island communities across history. Every kilogram of food, fuel, and building material had to be transported upward repeatedly. Strong winds, rough seas, and dangerous cliffs would have complicated every delivery, yet the fortress remained active. This suggests a level of organization often underestimated in discussions of early Pictish society. Maintaining such a site required planning, labor coordination, and sustained resource management. These are characteristics typically associated with complex political structures rather than loosely connected tribal groups. Another major mystery emerged through discoveries of Pictish symbol stones associated with Dunakaya. The stones contain distinctive carvings including crescents, geometric symbols, animals, and abstract designs. Similar symbols appear across eastern and northern Scotland. The challenge is that nobody has definitively deciphered them. Some researchers interpret the symbols as clan identifiers, others propose religious meanings, and some suggest they represent an early writing system. The remarkable consistency of these carvings across hundreds of kilometers indicates communication networks extending far beyond a single settlement, yet their precise meaning remains unknown. If Dunakaya was indeed an important early Pictish centre, it may have played a role in spreading these symbols. However, without written explanations, archaeologists can only speculate. Radiocarbon dating suggests occupation during the 2nd to 4th centuries AD, a period earlier than many traditionally recognised Pictish power centres. This finding challenges older assumptions about Pictish development. Constructing a fortified sea stack required surveying, transportation systems, labour organisation, and defensive planning. These capabilities imply a society more sophisticated than previously imagined. The comparison with contemporary Europe is revealing. During the same period, Roman engineers were constructing roads, bridges, and military installations throughout Britain. While the Picts left far fewer written records, sites like Dunakaya suggest they possessed their own specialised engineering traditions adapted to local conditions. Exactly how this knowledge developed remains unknown. Dunakaya may no longer exist in its original form. Coastal erosion has likely altered the cliffs, sea stacks, and access routes used by its ancient inhabitants. As a result, archaeologists may be reconstructing the fortress without key parts of its surrounding landscape. This loss could explain why some engineering solutions seem impossible today. The greatest obstacle to understanding Dunakaya may be that crucial evidence has already been destroyed by the ocean. What do you think was the most impressive achievement of Dunakaya? Building a fortress on an isolated sea stack, resisting centuries of coastal erosion, or maintaining life in one of the most inaccessible strongholds of ancient Scotland? Tap O Noth is a windswept hill rising 563 metres above sea level in Aberdeenshire, northeastern Scotland. What appears today to be a remote summit covered in grass and stone may actually conceal one of the greatest archaeological surprises ever discovered in early medieval Europe. At the centre of the mystery stands a question that remains unanswered even after decades of research. How did ancient builders create walls so hot that the stones themselves partially melted and fused together? The site was first recognised as an ancient hill fort during 19th century surveys, but its true significance only emerged through modern archaeological investigations. Recent LiDAR mapping, drone surveys, and excavations revealed something few researchers expected. Instead of a small defensive outpost, Tap O Noth appears to have been a vast settlement occupied during the Pictish period, roughly between the 5th and 7th centuries AD. Archaeologists identified the remains of approximately 800 circular timber structures spread across the hilltop and surrounding slopes. If all were occupied simultaneously, the population may have reached between 3,000 and 4,000 people, making it potentially one of the largest known settlements in northern Britain after the collapse of Roman authority. The greatest mystery of Tap O Noth concerns its remarkable vitrified walls. Unlike ordinary stone fortifications, portions of the defensive ramparts display evidence of vitrification, a process in which intense heat partially melts minerals within stone, causing them to fuse together into glass-like masses. The phenomenon is rare but not unique. More than 60 vitrified forts have been identified across Scotland, yet Tap O Noth remains among the most impressive examples. The problem is not the existence of vitrification itself. The problem is understanding how ancient people achieved it. Modern geological analysis suggests that many of the rocks used in the walls would require temperatures approaching 1,000 to 1,200 degrees Celsius before significant melting could occur. To appreciate the challenge, consider that a typical domestic fire rarely exceeds 600 degrees Celsius. Even many ancient industrial furnaces struggled to maintain temperatures above 1,000 degrees Celsius for extended periods. Producing such heat across a massive stone wall hundreds of meters long represents a completely different engineering challenge. Researchers have proposed several explanations. One theory suggests that enemy forces burned the fort during an attack, accidentally creating the vitrified sections. However, experiments indicate that an ordinary fire would not generate sufficient heat across such a large area. Another theory proposes that the builders intentionally vitrified the walls as a strengthening technique. This idea appears attractive because fused stone might seem stronger than ordinary masonry. Yet, experimental archaeology has produced mixed results. Some reconstructed vitrified walls actually became more brittle after heating. Furthermore, achieving vitrification would have required enormous quantities of timber. Estimates from experimental reconstruction suggest that several tons of wood might be needed to vitrify even a relatively small section of wall. Scaling that process to the size of Tap O Noth would have demanded an extraordinary logistical effort. The mystery becomes even deeper when compared with other ancient engineering achievements. The builders of the Roman aqueducts transported water across hundreds of kilometers, using gradients measured in centimeters per kilometer. The creators of Iron Age blast furnaces developed methods capable of producing temperatures high enough to smelt metal. Yet in both cases, archaeologists can identify the technology involved. At Tap O Noth, the evidence survives, but the exact method remains elusive. No written records explain how the fires were arranged, how airflow was controlled, or whether specialized structures were used to concentrate heat. The walls themselves preserve the result, but not the process. Another mystery involves the astonishing scale of the settlement. For generations, historians viewed post-Roman northern Scotland as a landscape dominated by scattered farming communities and small tribal centres. Tap O Noth challenges that assumption. The discovery of hundreds of buildings suggests a level of social organisation rarely associated with the Picts. Coordinating construction on such a scale would have required planning, labour management, and resource distribution comparable to urban centres elsewhere in Europe. The settlement's size raises difficult logistical questions. If the population approached 4,000 inhabitants, daily resource requirements would have been enormous. Modern estimates indicate that a community of this size would require several thousand litres of water each day merely for drinking and cooking. Additional water would be needed for livestock, craft production, and sanitation. Yet Tap O Noth occupies a hilltop location, lacking major natural water sources. Archaeologists have identified potential collection systems and nearby springs, but the full water management network remains unknown. Food supply presents an equally significant puzzle. Assuming an average caloric requirement of approximately 2,000 calories per person per day, the settlement would have required millions of calories every 24 hours. This demand implies extensive agricultural production across the surrounding valleys. The inhabitants must have maintained complex relationships with nearby farming communities, transportation networks, and storage facilities. However, the exact mechanisms supporting such a large population remain poorly understood. The engineering challenge of construction itself is another mystery. The summit stands more than half a kilometre above sea level and experiences strong winds, harsh winters, and difficult terrain. Every stone used in the fortifications had to be transported uphill. Thousands of timber beams had to be harvested, shaped, and carried to the site. Unlike Roman engineers, the builders left no manuals, no measurements, and no technical drawings. Nevertheless, they successfully erected one of the most imposing strongholds in northern Britain. Researchers also continue to debate how the settlement was organised. The distribution of structures suggests planning rather than random growth. Certain areas appear to contain clusters of buildings, while others remain open. Some archaeologists have suggested the existence of specialized districts dedicated to storage, craft production, or elite residence. If true, this would indicate a level of urban planning far beyond traditional views of early medieval Scotland. Yet excavation has only sampled a fraction of the site, leaving many questions unanswered. The strategic location of Tap O Noth introduces another layer of mystery. From the summit, observers can see vast stretches of Aberdeenshire. Visibility extends across valleys, hills, and potential communication routes. Such positioning may have allowed the transmission of signals between distant settlements. Throughout history, civilizations have used fire beacons, smoke signals, and reflective devices to communicate across long distances. Similar systems existed in Roman Britain, ancient Greece, and Imperial China. Whether Tap O Noth participated in a comparable network remains unknown, but its commanding position strongly suggests strategic significance. Perhaps the most fascinating mystery involves the Picts themselves. Despite centuries of study, much about their society remains obscure. They left behind symbol stones, monumental architecture, and evidence of extensive political organisation. Yet their language is only partially understood, and very few written records survive. Tap O Noth provides evidence of remarkable engineering capabilities, but almost none of the knowledge behind those achievements remains. Archaeologists can analyse charcoal samples, map structures with LiDAR, and study vitrified stone using microscopes and geochemical testing. What they cannot recover is the practical expertise that once guided construction. What do you think is the greatest mystery of Tap O Noth? The vitrified walls, the lost engineering knowledge, or the possibility that one of the largest settlements in early medieval Britain remained hidden in plain sight for centuries. Pulemalai Mound is the largest ancient monument ever built in Polynesia. Hidden within dense vegetation on the island of Savaii in Samoa, this massive stepped platform rises nearly 12 meters above the surrounding landscape and covers roughly 60 by 65 meters at its base. At first glance, it appears to be little more than a giant stone mound. Yet the deeper archaeologists investigate, the more questions emerge. How did a society without metal tools, wheeled transport, or written engineering manuals construct one of the largest stone monuments in the Pacific? Why was it built with such precision? And could its orientation reveal astronomical knowledge that has been forgotten for centuries? The site became known to the outside world during the 19th century, but systematic archaeological investigations did not begin until much later. Excavations conducted by researchers including Roger Green and later teams revealed that Pulemalai was not a natural hill. It was a carefully engineered structure built in multiple stages over many centuries. Beneath and around the mound, archaeologists discovered evidence of ancient habitation, ceremonial activity, and stone construction dating back hundreds of years before European contact. Yet despite decades of research, many of the site's most important secrets remain unresolved. The first mystery involves scale. Polynesian societies produced some of the most remarkable achievements in human history. Their navigators crossed thousands of kilometers of open ocean using stars, waves, winds, and environmental cues. Their canoes reached islands separated by vast stretches of the Pacific long before European explorers entered the region. Yet monumental stone architecture on the scale of Pulemalai is relatively rare in Samoa. The mound contains thousands of tons of basalt and volcanic stone arranged into a massive stepped platform. Even today, transporting such quantities of material through tropical terrain would require substantial planning and coordination. Researchers estimate that constructing a monument of this size would have demanded a large workforce, organized leadership, and long-term resource management. The challenge becomes even more impressive when considering the environmental conditions. Savaii receives heavy rainfall throughout much of the year. Tropical vegetation grows rapidly. Erosion constantly reshapes the landscape. Despite these challenges, Pulemalai has survived for centuries. The monument's durability suggests that its builders possessed a sophisticated understanding of stone engineering and landscape management. The second mystery concerns construction techniques. Unlike the Great Pyramid of Giza, which used carefully cut limestone blocks, Pulemalai was built primarily from volcanic stone gathered locally. Yet the builders still faced significant engineering challenges. The structure rises through a series of terraces that maintain stability despite centuries of weather exposure. Large retaining walls support enormous masses of stone and fill material. Modern engineers recognize that such structures require careful consideration of weight distribution, drainage, and slope stability. One of the greatest threats to any large earthen or stone platform is water infiltration. Rainwater trapped inside a structure can gradually weaken foundations and trigger collapse. The fact that Pulemalai remains standing suggests that its builders developed effective methods of drainage and load management. However, because no written records survive, archaeologists can only reconstruct these methods indirectly through excavation and structural analysis. The exact engineering principles employed by the builders remain largely unknown. The third mystery involves chronology. Evidence indicates that Pulemalai was not constructed in a single event. Archaeological layers suggest multiple phases of expansion and modification. Earlier structures may exist beneath later construction stages. This raises important questions about the transmission of technical knowledge. If the monument evolved over generations, builders would have needed to preserve architectural plans, construction methods, and ceremonial traditions across centuries. This phenomenon appears elsewhere in ancient history. The builders of Stonehenge modified their monument repeatedly over approximately 1,500 years. The inhabitants of Cahokia expanded Monk's Mound through multiple construction phases. The pyramid complexes of Mesoamerica similarly evolved across generations. Pulemale may represent a Polynesian example of the same process, where monumental architecture became a long-term project extending beyond the lifetime of any single ruler or community. The fourth mystery concerns the purpose of the structure itself. Archaeologists generally agree that Pulemale served an important ceremonial function. Artifacts discovered on the summit suggest ritual activity, elite gatherings, or religious events. Yet the sheer scale of the monument raises a fundamental question. Why build such an enormous platform simply to create elevated ceremonial space? Throughout human history, height has often been associated with authority, power, and connections to the supernatural. Mesopotamian civilizations constructed ziggurats. The Maya built pyramidal temples. Ancient Egyptians raised monumental pyramids visible across vast distances. In each case, elevation transformed architecture into a symbol of status and cosmic significance. Pulemale may have fulfilled a similar role within Samoan society, but exactly how it functioned within religious and political system remains uncertain. The fifth and perhaps most fascinating mystery involves astronomy and spatial orientation. This aspect of Pulemale has attracted increasing attention because it connects the monument to one of the greatest achievements of Polynesian civilization: navigation. The Polynesians were among the finest navigators the world has ever known. Long before compasses became common, they crossed enormous distances across the Pacific Ocean. Experimental voyages conducted during the 20th century demonstrated that traditional navigation techniques could successfully guide vessels across thousands of kilometers using celestial observations alone. Navigators memorized the rising and setting positions of stars, tracked seasonal changes in the sky, and interpreted wave patterns generated by distant islands. Given this extraordinary astronomical knowledge, some researchers have wondered whether Pulemale's orientation may reflect intentional alignment with celestial events. Certain Polynesian ceremonial sites exhibit spatial relationships connected to solar cycles, star paths, or culturally important directions. Although no definitive astronomical alignment has yet been proven at Pulemale, the possibility remains intriguing. The monument occupies a prominent position within the landscape. From elevated locations, observers could monitor the movement of the sun across the horizon and track seasonal changes. In societies dependent upon navigation, agriculture, and ceremonial calendars, accurate knowledge of celestial cycles possess practical as well as spiritual value. Determining the arrival of seasonal weather patterns, organizing voyages, and coordinating rituals all benefited from careful observation of the sky. This mystery becomes even more compelling when compared with other ancient sites. Stonehenge appears linked to solstitial events. The Temple of Kukulkan at Chichen Itza produces famous shadow effects during equinoxes. Numerous Polynesian navigational traditions preserve detailed astronomical knowledge despite the absence of written records. If Pulemale incorporated similar principles, it could represent physical evidence of a sophisticated observational tradition that has largely vanished. The challenge is that astronomy leaves few archaeological traces. Stone walls survive, artifacts survive, celestial knowledge does not. Unless clear alignments or supporting traditions remain, reconstructing ancient astronomical systems becomes extraordinarily difficult. As a result, the relationship between Ptolemai and the sky remains one of the site's most intriguing unanswered questions. The sixth mystery is the society that built Ptolemai. Such a large monument required leadership, organized labor, food production, and cooperation. Each stone and terrace reflects careful planning, yet archaeologists still know little about the political system that made it possible. This is a common challenge in archaeology. The monuments remain, but the societies behind them are often poorly understood. Like the builders of Easter Island's Moai, Nan Madol, and Great Zimbabwe, the people who built Ptolemai left impressive structures but few clues about how their society functioned. What do you think was the true purpose of Ptolemai Mound? Was it a ceremonial centre, an astronomical observatory, a symbol of political power, or something we have not yet discovered? Share your thoughts in the comments below. Castell Henllys is an Iron Age hill fort in Pembrokeshire, Western Wales. Archaeologists first identified the site's importance through excavations conducted between the 1980s and 1990s, revealing defensive earthworks, roundhouses, storage areas, and evidence of long-term occupation dating primarily between the 4th century BC and the 1st century AD. Unlike most Iron Age sites in Britain, Castell Henllys became the focus of one of archaeology's most ambitious reconstruction projects. Researchers rebuilt several structures directly above their original foundations to understand how Iron Age communities lived, built, and engineered their environment. Yet the more archaeologists reconstructed, the more mysteries emerged. Rather than answering every question, Castell Henllys exposed how much technological knowledge has been lost over the past 2,000 years. The first mystery involves the engineering of the roundhouses themselves. Excavations revealed circular buildings measuring up to 13 meters in diameter. At first glance, these structures appear simple, consisting mainly of timber posts, woven walls, and thatched roofs. However, experimental archaeology quickly demonstrated that constructing such buildings is far more difficult than expected. A roundhouse roof can weigh several tons once covered with thick layers of thatch. Every supporting beam must distribute weight evenly while resisting strong Atlantic winds. Modern engineers can model structural loads using software, but Iron Age builders possessed no computers, no written blueprints, and no surviving technical manuals. When reconstructed at Castell Henllys, archaeologists discovered that even minor mistakes in roof geometry could destabilize the entire structure. The builders somehow understood how to position dozens of rafters at precisely the correct angles. Similar challenges appear in the reconstruction of prehistoric buildings across Europe, from the Celtic settlements of France to the Iron Age villages of Germany. Yet no one knows exactly how this geometric knowledge was transmitted. Some researchers suggest the use of rope-based measuring systems, while others propose highly specialized master builders whose knowledge passed orally through generations. The evidence remains inconclusive. The second mystery concerns weather resistance. Western Wales experiences frequent rainfall, strong winds, and harsh winter storms. Modern houses rely on waterproof membranes, industrial fasteners, treated timber, and synthetic materials to remain dry. Iron Age builders possessed none of these technologies. Nevertheless, reconstructed roofs at Castell Henllys have demonstrated remarkable durability. Properly constructed thatched roofs can survive for decades while shedding enormous volumes of rainwater. This raises an important engineering question. How did ancient builders determine the ideal roof pitch, thickness, and material density? Experimental studies have shown that a roof angle that is too shallow allows water penetration, while excessive weight can threaten structural stability. Achieving the correct balance requires practical knowledge accumulated through countless observations. Yet the process by which Iron Age craftsmen acquired and standardized this expertise remains largely unknown. The knowledge existed. The instructions did not survive. A third mystery centers on the hill fort's defensive earthworks. Castel Henlys occupies a naturally defensible spur overlooking steep valleys. The inhabitants enhanced these advantages by constructing ramparts, banks, and ditches. Archaeological surveys indicate that large volumes of soil were moved during construction. Such projects required planning on a scale often underestimated by modern observers. Recent engineering studies of ancient earthworks demonstrate that slope angles, soil composition, drainage, and erosion resistance significantly affect long-term stability. What is remarkable is that portions of Castel Henlys' defences have survived for more than 2,000 years, despite constant exposure to rainfall and environmental change. This achievement suggests a practical understanding of soil mechanics. Yet there is no evidence that Iron Age communities possessed anything resembling formal engineering mathematics. How they determined optimal ditch profiles, embankment dimensions, and drainage systems remains uncertain. The mystery becomes even more intriguing when compared with other ancient engineering traditions. Roman military engineers documented aspects of fortification design. Medieval builders left manuscripts describing construction methods. The people of Castel Henlys left almost nothing written behind. Their earthworks survived better than the knowledge that created them. Another unresolved puzzle involves timber procurement. Modern reconstructions reveal that a single large roundhouse requires a surprisingly large quantity of wood. Not just any wood would suffice. Builders needed trees of specific dimensions, suitable flexibility, and predictable durability. Some timbers had to resist rot. Others had to support substantial loads. Environmental analysis suggests that Iron Age communities actively managed woodland resources. If true, this would imply a sophisticated understanding of long-term sustainability. A settlement that harvested trees without planning would eventually exhaust local resources. Yet Castel Henlys appears to have remained occupied for centuries. How did its inhabitants organize woodland management? Did they intentionally cultivate construction timber? Did they understand seasonal cutting cycles that reduced moisture content and improved durability? The archaeological evidence provides hints but no definitive answers. The fifth mystery concerns indoor air management. Every reconstructed roundhouse contains a central hearth. Fire provided heat, cooking facilities, light, and social focus. Yet the buildings lack conventional chimneys. To modern observers, this creates an obvious problem. How did people avoid dangerous smoke accumulation? Experimental studies conducted within reconstructed structures have produced surprising results. Smoke behavior depends on roof geometry, doorway placement, airflow patterns, and thatch permeability. In some cases, smoke rises into upper roof spaces before gradually filtering outward through the thatch. In others, carefully positioned openings influence circulation patterns. Researchers continue to debate which mechanisms were most important. What makes the mystery fascinating is that Iron Age builders apparently achieved acceptable living conditions without scientific instruments, airflow calculations, or formal architectural theory. They solved a complex environmental engineering challenge through knowledge that was never written down. Perhaps the most significant mystery involves labor organization. Archaeological excavations reveal that Castel Henlys was not the work of isolated families. Constructing defensive earthworks, gathering timber, producing building materials, and maintaining infrastructure required coordinated effort. Modern reconstruction projects demonstrate the enormous labor investment involved. Who directed these projects? Did specialized architects exist? Were there master builders responsible for transferring technical knowledge? How were large groups coordinated without written plans or administrative records? These questions remain difficult to answer because archaeological evidence preserves structures far more effectively than social systems. Comparisons with other prehistoric centres highlight the scale of the problem. The builders of Stonehenge transported stones weighing up to 25 tons. The creators of the Hüneberg Hill Fort in Germany constructed complex defensive systems. The inhabitants of Castel Henles may not have moved megaliths, but they demonstrated equally impressive mastery of construction, logistics, and environmental adaptation. In every case, the physical remains survived while much of the organizational knowledge disappeared. What do you think was the greatest achievement of Castel Henles? The engineering of its massive roundhouses, the durability of its defenses, or the lost knowledge that allowed Iron Age builders to master construction without written plans? Share your thoughts in the comments below. Located in County Roscommon in Western Ireland, Rathcrogan covers more than 6 square kilometres and contains over 240 recorded archaeological monuments. Unlike famous ancient centres such as Stonehenge, Newgrange or Avebury, the site appears almost invisible from the ground. There are no towering stone circles, no massive pyramids, and no surviving palaces. Yet beneath the fields lies evidence of a vast ceremonial complex that functioned as one of Iron Age Ireland's most important royal and religious centres. Modern surveys have revealed hidden earthworks, buried structures, ritual avenues, and underground features that continue to challenge archaeologists. The greatest mystery is not what survives, but how an ancient society created such a sophisticated landscape while leaving behind so few clues about the engineering knowledge that made it possible. Rathcrogan was first recognised as an important archaeological site during antiquarian investigations in the 18th and 19th centuries. However, its true scale remained unknown until aerial photography, geophysical surveys, and modern archaeological investigations began revealing what lay beneath the surface. The complex is centred on Rathcrogan Mound, a large circular enclosure approximately 89 metres in diameter. Excavations and surveys have shown that this mound was not an isolated monument, but part of an enormous network of ceremonial and political sites spread across the surrounding landscape. Archaeologists from the Archaeological Survey of Ireland, together with university researchers, have used magnetometry, LIDAR, and ground-penetrating investigations to identify dozens of previously unknown structures hidden underground. The first great mystery concerns the planning of the entire landscape. Rathcrogan was not constructed as a single monument. It was an integrated ceremonial system extending across several kilometres. Numerous enclosures, burial sites, assembly areas, and ritual locations appeared deliberately connected. Such coordination required surveying, organisation, and long-term planning. Modern engineers rely on GPS satellites, laser scanners, and digital mapping software to coordinate projects covering large areas. Iron Age builders possessed none of these technologies, yet the arrangement of monuments suggests a detailed understanding of landscape management. Archaeologists continue to debate how these ancient surveyors measured distances, established alignments, and coordinated construction across such a vast territory. Similar questions have been raised at Stonehenge and Avebury, but Rathcrogan presents an even greater challenge because so much of the evidence remains hidden underground. One of the most intriguing discoveries involves the multiple circular earthworks surrounding the central mound. Geophysical surveys have revealed buried rings, ditches, and enclosure systems that are difficult to detect on the surface. Some of these features required moving thousands of cubic meters of soil. Experimental archaeology demonstrates that constructing large earthworks using wooden tools, antler picks, and human labour would have demanded enormous effort. Researchers estimate that major prehistoric earthworks elsewhere in Europe required tens of thousands of labour hours. Rathcrogan raises the question of how labour was organised, supplied, and directed. The engineering challenge was not merely excavation but coordination. Large workforces require food, logistics, leadership, and planning. Yet almost no written record survived to explain how these projects were managed. Another mystery involves the remarkable durability of the earthworks themselves. Ireland's climate presents significant challenges to preservation. Annual rainfall often exceeds 1,000 millimetres in many regions, creating conditions favourable for erosion. Despite this, portions of the Rathcrogan complex remain recognisable after nearly 2,000 years. The builders appear to have selected locations and construction methods that minimised environmental damage. Modern geotechnical engineers study drainage, soil stability and erosion resistance using sophisticated computer models. Ancient builders relied entirely on observation and accumulated experience. Whether their success resulted from generations of practical experimentation or from specialized engineering traditions remains unknown. The most famous location within the Rathcrogan complex is Ovinagat, often translated as the Cave of the Cats. This underground chamber occupies a central place in Irish mythology and has long been associated with the other world. According to medieval traditions, supernatural beings emerged from the cave during the festival of Samhain. Archaeologically, Ovinagat presents a fascinating technical puzzle. The entrance consists of a stone-built passage leading into a natural limestone cave. Several stones contain Ogham inscriptions dating from the early medieval period. While natural caves exist throughout Ireland, Ovinagat appears to have been deliberately modified and incorporated into a larger ceremonial system. The engineering significance of Ovinagat remains poorly understood. The entrance passage was carefully constructed using large stone slabs, creating a controlled transition between the surface world and the underground chamber. Researchers have noted unusual acoustic properties within parts of the cave. Sound can echo, amplify, and distort in ways that create striking sensory experiences. Similar acoustic phenomena have been documented at prehistoric sites, including Newgrange in Ireland and certain ritual chambers in Malta. Whether the builders intentionally selected Ovinagat because of its acoustic characteristics remains unknown. If they did, it would suggest a sophisticated understanding of how architecture and natural geology could influence human perception during ceremonies. The relationship between mythology and archaeology introduces another unresolved mystery. Medieval Irish texts describe Rathcrogan as the royal seat of the kings of Connaught and connect the landscape to numerous legendary events. While archaeology confirms that the region served as an important centre during the Iron Age, determining how much of the mythology reflects historical reality remains difficult. Across the ancient world, ceremonial centres often accumulated myths over centuries. Sites such as Delphi in Greece, the Temple of Karnak in Egypt, and Teotihuacan in Mexico became intertwined with stories that blurred the line between history and legend. Rathcrogan appears to belong to the same category. The challenge is separating symbolic narratives from evidence of actual activities conducted at the site. A further mystery concerns the structures that no longer exist. Excavations have identified evidence of large timber buildings through post holes, soil discoloration and carbonized remains. Wood dominated construction throughout Iron Age Ireland. Unlike stone architecture, timber rarely survives for long periods in the Irish climate. As a result, archaeologists possess only fragmentary evidence for what may once have been impressive ceremonial halls, assembly structures, and ritual buildings. This creates a problem similar to that faced at many prehistoric sites throughout northern Europe. The foundations survive while the architecture disappears. Reconstructing these buildings requires combining excavation data, experimental archaeology, and comparisons with better preserved structures elsewhere. Recent geophysical investigations have revealed that numerous archaeological features remain buried beneath the landscape. Magnetometer surveys can detect subtle changes in soil magnetism caused by ditches, hearths, pits, and buried structures. These technologies have transformed understanding of Rathcrogan. In many cases, researchers can map entire archaeological features without excavation. Yet every discovery generates new questions. Some anomalies suggest structures whose purpose remains uncertain. Others indicate activity areas unlike anything previously identified in Iron Age Ireland. The more the site is studied, the more complex it appears. Comparison with other prehistoric ceremonial landscapes highlights Rathcrogan's uniqueness. Stonehenge occupies approximately 12 square kilometres within a broader ritual landscape. Avebury contains massive stone circles and earthworks visible from great distances. Newgrange preserves a monumental passage tomb more than 5,000 years old. Rathcrogan differs because much of its complexity is hidden beneath the ground. Rather than monumental stone architecture, its craters shaped an entire landscape through earthworks, ritual spaces, and carefully selected natural features. The result is a ceremonial centre that remained largely invisible until modern technology began revealing its true scale. In antiquity, the settlement of Awara stood in the arid deserts of southern Jordan between Petra and Aqaba. At first glance, the site appears to be little more than a collection of ruins surrounded by barren land. Yet beneath the sand lies one of the most overlooked engineering mysteries of the ancient world. Archaeologists have discovered evidence that this settlement survived for nearly 1,000 years in a region receiving less than 100 millimeters of annual rainfall. Even more astonishing, its inhabitants developed a water management system capable of sustaining agriculture, trade, military garrisons, and thousands of people in an environment where permanent settlement should have been nearly impossible. The site first attracted serious archaeological attention during the 20th century, and systematic excavations led by teams from North American and Jordanian institutions revealed Nabatean, Roman, Byzantine, and early Islamic remains. What researchers uncovered was not merely another desert town, but traces of a sophisticated hydraulic network that transformed one of the harshest environments in the Near East into a functioning urban centre. The discovery raised a question that remains only partially answered today. How did ancient engineers achieve such extraordinary control over water without modern instruments, hydrological models, or advanced surveying equipment? The first mystery concerns the scale of water collection itself. Hamaima was founded during the Nabatean period, likely in the 1st century BC under the reign of King Aretas III or his successors. The Nabateans are best known for Petra, but Hamaima demonstrates that their greatest technological achievement may not have been monumental architecture. It may have been hydraulic engineering. Archaeological surveys have identified reservoirs, cisterns, channels, pipelines, and aqueduct systems extending across the surrounding landscape. These installations captured seasonal rainfall, diverted runoff, stored water underground, and distributed it throughout the settlement. The challenge becomes clear when compared with other ancient civilizations. The Romans built famous aqueducts, but many relied on relatively stable springs and rivers. Egyptian civilization flourished beside the Nile, while Mesopotamian cities developed between the Tigris and Euphrates. Humaima had none of these advantages. The settlement existed in a region where water was scarce, unpredictable, and often separated from habitation zones by kilometers of difficult terrain. Yet archaeological evidence suggests that the inhabitants created a system capable of functioning for centuries. The second mystery involves surveying accuracy. Modern engineers use satellite positioning systems, laser measurements, topographic maps, and computer simulations to design long-distance water networks. Ancient Nabatean engineers possessed none of these tools. Nevertheless, the channels discovered around Humaima maintained gradients precise enough to transport water efficiently across uneven desert landscapes. If a channel's slope is too steep, erosion destroys the structure, while if it is too shallow, water stagnates and sediment accumulates. Maintaining optimal flow across long distances requires remarkable precision. Researchers studying Nabatean hydraulic systems at Petra and Humaima have repeatedly noted the sophistication of their designs. Some channels followed natural contours with minimal energy loss, while others incorporated settling basins that reduce sediment accumulation. The engineering principles resemble solutions employed in much later hydraulic systems, yet almost no technical documents survive explaining how these calculations were performed. The knowledge appears to have vanished while the infrastructure remained. The third and perhaps greatest mystery involves flash flood management. This is where Humaima becomes truly extraordinary. Most people imagine deserts as places without water, but in reality deserts often experience violent and highly destructive floods. Months or even years can pass with minimal rainfall, and then a sudden storm can release enormous quantities of water within a few hours. These flash floods move rapidly through dry valleys known as wadis, carrying rocks, sediment, and debris capable of destroying settlements. Modern flash flood prediction requires meteorological monitoring, rainfall models, hydrological simulations, and extensive engineering analysis. Yet the Nabateans faced the same challenge more than 2,000 years ago. Instead of merely surviving these floods, they appear to have turned them into a resource. Archaeological investigations around Humaima reveal an interconnected system designed not only to collect water, but also to regulate extreme flood events. Channels intercepted runoff before it became destructive. Reservoirs captured sudden surges. Diversion structures redirected excess flow, and storage facilities preserved water long after seasonal storms ended. In effect, the inhabitants transformed a dangerous environmental threat into the foundation of urban survival. The scale of this achievement becomes apparent when considering the unpredictability of desert hydrology. Flash floods do not occur at regular intervals, and their intensity varies dramatically from one event to another. Designing infrastructure capable of handling both drought and sudden flooding requires an understanding of water behavior accumulated through generations of observation. Yet researchers still debate how Nabatean engineers gathered and transmitted such knowledge. No surviving manuals describe their methods, no engineering treatises explain their calculations, and no detailed instructions reveal how flood control structures were designed. The physical evidence demonstrates that the system worked, but the intellectual framework behind it remains largely invisible. The fourth mystery concerns long-term sustainability. Many ancient settlements flourished briefly before environmental stress forced abandonment. Humaima endured through multiple political eras. Nabatean occupation was followed by Roman administration, Byzantine communities, and early Islamic inhabitants. The settlement remained viable for centuries despite changing governments, economies, and populations. This continuity suggests that the hydraulic system was not merely effective but maintainable. Reservoirs required cleaning, channels required repairs, and flood control installations required monitoring. Such activities imply the existence of trained specialists responsible for preserving critical infrastructure. Yet archaeology has revealed little about who these individuals were or how technical knowledge passed from one generation to another. The disappearance of this expertise echoes patterns seen elsewhere in history. Roman concrete survived millennia while many of its production techniques were forgotten. The builders of the Great Pyramid left monumental structures but few engineering explanations. The creators of the Antikythera mechanism produced an astonishing astronomical device, while leaving almost no documentation of its construction. Humaima may represent another example of technological knowledge vanishing while its results remain visible. The fifth mystery involves environmental adaptation on a level that still impresses modern researchers. Today, water scarcity affects hundreds of millions of people worldwide. According to United Nations estimates, large portions of the global population experience severe water stress during parts of the year. Modern societies address this challenge using pumps, sensors, satellites, desalination plants, and computer-controlled distribution networks. The inhabitants of Humaima achieved a comparable objective using stone channels, gravity, reservoirs, and accumulated experience. Their solutions were entirely dependent upon understanding local geography, rainfall patterns, soil behavior, and flood dynamics. The sophistication of these systems suggests that Nabatean engineering was not a secondary achievement supporting their civilization. It may have been the very foundation upon which their civilization depended. Excavations continue to reveal additional details about the site's hydraulic infrastructure, but major questions remain unanswered. How did engineers determine optimal channel gradients without modern surveying instruments? How did they predict flood behavior in an environment characterized by extreme variability? How did they calculate storage capacity sufficient to survive prolonged droughts? How was technical knowledge transmitted across centuries without leaving substantial written records? And perhaps most importantly, how much of their expertise disappeared forever when the communities that maintained these systems eventually declined? Lapaha Royal Tombs is one of the most important archaeological sites in the Pacific, yet it remains one of the least understood. Located on the northern coast of Tongatapu, the main island of the Kingdom of Tonga, Lapaha served as the political and ceremonial centre of the Tusi Tonga dynasty for centuries. Archaeological investigations beginning in the 19th century revealed dozens of royal tombs known as langi, monumental stone structures built for the rulers of a maritime empire that once dominated much of Polynesia. At first glance, the tombs appear simple compared with the pyramids of Egypt or the temples of the Maya. However, a closer examination reveals engineering problems that archaeologists still struggle to explain. How did a society without metal tools, wheeled vehicles, or draft animals transport and assemble thousands of tons of stone? How did builders maintain remarkable precision while working with coral limestone? And how did the technical knowledge behind these achievements disappear almost completely? The most visible mystery at Lapaha is the construction of the royal tombs themselves. More than 20 major langi have been identified, with some consisting of multiple tiers of massive limestone blocks. The largest structures stretch over 50 meters in length and contain stones weighing between 10 and 40 tons. These blocks were quarried from coral limestone deposits located several kilometers away from the construction sites. Moving a single 30-ton stone would be challenging even with modern machinery. Yet the builders of Lapaha accomplished this centuries before European contact. The transportation problem remains one of the greatest engineering mysteries in Polynesian archaeology. Unlike ancient Egypt, where builders could use the Nile as a transportation corridor, Tonga consisted of islands separated by lagoons, reefs, and shallow coastal waters. Archaeologists believe the stones were moved using a combination of sledges, rollers, canoes, and large rafts. Experimental studies suggest that hundreds of workers may have been required to move a single block. However, no surviving records explain the exact methods. The challenge becomes even more remarkable when compared with other ancient civilizations. The famous stones of Stonehenge weigh up to 25 tons. Many of the blocks used in the Lapahar tombs fall within the same weight range, yet the builders operated in an island environment with fewer available resources and no evidence of advanced lifting devices. The mystery deepens when examining the precision of the stonework. Coral limestone is softer than granite, but shaping large blocks into flat surfaces still requires considerable skill. The stones of the Langi were carefully cut, leveled and fitted together to create stable platforms capable of supporting enormous weight. Some joints display a degree of accuracy that suggests standardized construction methods. This raises a fundamental question. How did Tonga's builders achieve such consistency without metal chisels or formal engineering manuals? Researchers studying traditional Polynesian stoneworking techniques have proposed that basalt tools were used to shape the limestone. Experimental archaeology demonstrates that basalt adzes can cut coral rock effectively. Yet experiments also show that producing the required level of precision is extremely labor-intensive. The amount of labor invested in each tomb may have been enormous. Some archaeologists estimate that major construction projects required thousands of workers and many years of coordinated effort. This suggests the existence of a highly organized political system, capable of directing large labor forces over long periods. Another mystery involves the construction of multi-tiered tombs. Several langi consist of stacked stone platforms rising several meters above ground level. Building such structures required lifting heavy blocks onto elevated levels with remarkable accuracy. No physical evidence of cranes, pulley systems, or large lifting frameworks has been discovered. Most theories suggest the use of earthen ramps similar to those proposed for Egyptian pyramids. Workers may have gradually raised stones using timber levers and inclined surfaces before removing the ramps after completion. The problem is that no direct archaeological evidence confirms this process. The engineering solution remains largely speculative. The organization behind these projects presents another puzzle. Large-scale stone construction requires more than technical skill. It requires administration, logistics, food production, and labor management. During the height of the Tui Tonga Empire between approximately AD 1200 and 1500, Tonga exerted influence across a vast area of the Pacific. Archaeological evidence indicates connections with Samoa, Fiji, Wallis, Futuna, and other island groups. Maintaining such a network demanded sophisticated maritime capabilities. The same society that built the royal tombs also managed long-distance voyages across thousands of kilometers of open ocean. This leads directly to another unresolved mystery. How did navigators sustain an empire without maps, compasses, or written instructions? Traditional Polynesian navigation relied on stars, wave patterns, ocean swells, bird movements, cloud formations, and environmental observation. Modern navigators often require instruments to achieve similar accuracy, yet Polynesian sailors crossed distances that rivaled some of the greatest maritime achievements in history. The navigational knowledge that supported the Tui Tonga Empire was likely essential to transporting materials, coordinating political alliances, and maintaining communication throughout the region. Unfortunately, much of this expertise vanished before it could be fully documented. One of the most intriguing aspects of Lapahar is its relationship with other monumental structures in Tonga. Not far from the royal tomb stands Ha'amonga, a Maui, a trilithon composed of 3 giant coral limestone blocks. The structure resembles, in a broad sense, the trilithons of Stonehenge. The 2 vertical stones stand approximately 5 meters high, while the horizontal lintel weighs around 10 tons. Scholars continue debating its purpose. Some view it as a ceremonial gateway. Others suggest astronomical functions connected to seasonal observations. Regardless of its exact role, the monument demonstrates that Tonga's builders possessed the ability to transport and position massive stones with considerable precision. The scale of construction at Lapaha also challenges long-standing assumptions about Pacific societies. For many years, European observers portrayed Polynesian cultures as relatively simple island communities. Archaeology has increasingly overturned this perception. The royal tombs reveal large-scale engineering, political centralization, organized labor systems, and extensive regional influence. In some respects, the logistical complexity behind Lapaha can be compared to that of major centers in ancient Europe or Southeast Asia. The difference is that most of Tonga's knowledge was transmitted orally rather than through written records. This disappearance of knowledge may be the greatest mystery of all. The builders understood quarrying, transportation, surveying, construction, navigation, and political organization. They coordinated projects involving thousands of tons of stone. They maintained maritime networks across vast areas of the Pacific. Yet almost none of the technical explanations survive. There are no architectural blueprints, engineering manuals, construction diagrams, or written descriptions of building methods. Among the best preserved ceremonial complexes in Tahiti, French Polynesia, Marae Rahurahu stands as a remarkable example of Polynesian sacred architecture. Located in the district of Paia on the western coast of Tahiti Nui, the site was documented by European visitors during the 18th and 19th centuries and later restored in the 1950s, based on archaeological investigations and surviving traditional knowledge. At first glance, it appears to be a simple stone platform surrounded by open ground. Yet beneath that apparent simplicity lies one of the most intriguing engineering mysteries in Polynesian history. How did a civilization without metal tools, wheeled transport, or written technical manuals create monumental ceremonial architecture across an ocean, covering millions of square kilometers? The first mystery is the engineering precision of the marae itself. Arahuhu consists of a large stone platform known as an ahu, constructed from carefully arranged basalt blocks. Some stones weigh hundreds of kilograms, while larger blocks may approach several tons. Unlike many ancient civilizations, the Polynesians possessed neither iron chisels nor bronze tools. Their technology relied largely on stone adzes, coral files, wooden implements, and fiber ropes. Despite these limitations, the builders created remarkably stable structures capable of surviving in a tropical environment characterized by heavy rainfall, earthquakes, vegetation growth, and centuries of weathering. Modern engineers understand that constructing a durable stone platform requires more than stacking rocks. Foundations must remain stable under varying loads. Surface drainage must prevent water accumulation. Stone blocks must be selected, transported, and fitted in ways that minimize structural weakness. At Arahurehu, the platform has survived centuries despite exposure to environmental conditions that rapidly destroy organic materials. Archaeologists can measure the dimensions of the structure, but the practical knowledge that guided its construction has largely disappeared. The builders left no written instructions explaining how foundations were prepared, how stones were selected, or how construction teams organized their work. The mystery becomes even more significant when Arahurehu is compared with other ceremonial centers throughout Polynesia. Similar moraes appear across Tahiti, Raiatea, Bora Bora, the Cook Islands, and numerous other islands separated by thousands of kilometres of open ocean. Although local variations exist, the overall architectural concepts remain remarkably consistent. Platforms, sacred spaces, ceremonial boundaries, and ritual arrangements follow patterns recognisable across much of eastern Polynesia. This raises a difficult question. How did architectural knowledge spread across such enormous distances without a written language? The Polynesian Triangle stretches across roughly 10 million square kilometres of ocean. For comparison, this area is larger than the entire continental United States. Maintaining architectural traditions over such distances would be challenging even with modern communication systems. Yet Polynesian societies preserved shared construction principles for centuries. Researchers believe knowledge was transmitted orally through specialists, priests, navigators, and master builders. However, exactly how complex engineering information remained consistent across generations remains one of the least understood aspects of Polynesian civilization. The second major mystery involves transportation technology. Every stone visible at Arahurahu had to be extracted, moved, and positioned by human labour. No evidence suggests the use of wheels. Polynesia possessed no draft animals comparable to horses, oxen, or camels. The islands also lacked the extensive road systems that supported construction projects in ancient Rome or Imperial China. Experimental archaeology demonstrates that large stones can be moved using ropes, wooden rollers, sledges, and coordinated labour. Yet proving possibility is not the same as explaining reality. Researchers still debate the exact methods used by Polynesian builders. How many workers were required? What organisational system coordinated the labour? How were heavy stones manoeuvred through uneven tropical terrain? The absence of written records leaves many of these questions unanswered. The challenge becomes even more remarkable when viewed within the broader context of Polynesian engineering. On Easter Island, known today as Rapa Nui, enormous moai statues weighing up to 80 tons were transported across the landscape. At Nan Madol in Micronesia, builders moved basalt columns weighing several tons to construct artificial islets and monumental walls. Across Polynesia and the wider Pacific, societies repeatedly demonstrated an ability to manipulate large quantities of stone despite technological limitations that modern observers often underestimate. Arahurahu forms part of this larger pattern of unexplained engineering capability. The third mystery concerns astronomical knowledge. Polynesian navigation remains one of the greatest achievements in human history. Long before modern instruments, navigators crossed thousands of kilometres of open ocean using stars, ocean swells, winds, clouds, and wildlife behaviour. Recent experimental voyages conducted by traditional navigation societies have demonstrated that these methods are not legends. They work. The famous voyaging canoe Hokulea successfully sailed thousands of kilometres using traditional navigation techniques, proving that ancient Polynesian navigators possessed extraordinarily sophisticated environmental knowledge. This raises an important question regarding sites such as Arahurahu. Were moraes simply religious centres, or did they also function as repositories of navigational knowledge? Several Polynesian ceremonial sites appear aligned with solar events, star paths, or significant directions associated with navigation. Some researchers propose that sacred architecture may have served multiple functions simultaneously: religious, political, educational, and astronomical. If true, Arahurahu may represent more than a ceremonial platform. It may have been part of a knowledge system supporting long-distance ocean exploration. The problem is that much of this knowledge vanished before systematic scientific documentation became possible. European contact during the 18th century triggered dramatic social transformations throughout Polynesia. Population decline, disease, missionary activity, political change, and cultural disruption affected traditional institutions. Knowledge that had accumulated over centuries began disappearing within only a few generations. The fourth mystery involves social organization. Large construction projects require more than technical skill. They require leadership, logistics, food production, labor management, and long-term planning. Every stone at Arahurahu represents human effort. Every construction phase requires coordination among workers, craftsmen, priests, and community leaders. Modern archaeological surveys indicate that many Polynesian societies supported surprisingly complex political systems. Population estimates for parts of eastern Polynesia suggest communities capable of organizing large-scale collective labor. Yet archaeologists still struggle to reconstruct exactly how authority functioned. Who designed marae? Were there specialist architects? Did master builders travel between islands? Was technical knowledge restricted to elite groups? These questions remain largely unresolved because the institutions responsible for preserving the knowledge disappeared while the monuments survived. What do you think is the greatest mystery of Arahurahu? The lost construction techniques, the vanished navigation knowledge, or the society that preserved engineering traditions across the vast Pacific Ocean without written records? Standing on a rocky peninsula overlooking the Moray Firth in northeastern Scotland, Burghead Fort was once a massive fortified centre built by the Picts, an ancient people who dominated northern Scotland during the early Middle Ages. Its true scale remained hidden for centuries, and what survives today is only a fraction of the original monument. Much of the fort was destroyed during the construction of the modern town of Burghead between 1805 and 1809. Yet archaeological discoveries suggest that what was lost may have been one of the largest and most sophisticated Pictish engineering projects ever undertaken. The mystery begins with its discovery. Although local people had long known of unusual earthworks and carved stones around Burghead, systematic archaeological investigations did not begin until the 19th century. Early records described enormous ramparts, defensive walls, and strange carved stone slabs depicting bulls. Modern excavations, geophysical surveys, and aerial studies have revealed that the fort once covered approximately 3 hectares and was protected by a series of massive defensive systems. Archaeologists now believe Burghead was not merely a military outpost, but one of the most important political and ceremonial centres in Pictland. What immediately puzzles researchers is the sheer scale of construction. The fort occupied a narrow headland surrounded on 3 sides by steep cliffs dropping directly into the sea. The only accessible land approach was blocked by enormous ramparts and ditches. Historical descriptions recorded walls up to 6 meters thick, built using vast quantities of stone. Even today, constructing such defences on a windswept coastal promontory would require significant planning, labour coordination, and engineering knowledge. The numbers involved are remarkable. Estimates suggest thousands of tons of stone had to be quarried, transported, shaped, and assembled. Unlike Roman forts, whose construction methods are documented through military records, Burghead was built by a society that left almost no written technical documentation. Archaeologists therefore face a fundamental mystery. How did the Picts organise labour on such a scale? Comparisons with other contemporary sites make the problem even more intriguing. During the 8th and 9th centuries, when Burghead was likely at its peak, many European fortifications were considerably smaller. Even several known royal centres in Britain occupied less defended space. Yet Burghead appears to have combined military defences, ceremonial functions, residential areas, and possible administrative facilities within a single complex. Such complexity suggests a level of political organization that historians may have underestimated. One of the greatest engineering mysteries concerns the fort's location itself. The headland appears almost perfectly chosen from a defensive perspective. The cliffs provided natural protection against attack, while offering extensive visibility across the Moray Firth. Modern military analysts often emphasize the importance of terrain selection, visibility, supply access, and defensibility. Berghead seems to satisfy all these requirements simultaneously. The question is how the builders achieved such optimization without maps, aerial surveys, satellite imagery, or modern surveying equipment. Today, engineers use drones and digital elevation models to evaluate defensive positions. The Picts relied entirely on observation, experience, and accumulated knowledge. Yet their choice of location rivals many later medieval fortifications designed with far more advanced tools. Another mystery involves coastal engineering. Berghead was constructed in one of the harshest maritime environments in Scotland. The North Sea produces powerful storms, salt spray, and relentless erosion. Geological studies show that coastal erosion can dramatically reshape cliff systems over centuries. Despite these conditions, major portions of the site survived for over 1,000 years. Researchers believe the builders intentionally incorporated natural rock formations into the defensive system. This required an understanding of local geology and structural stability. Modern engineers evaluate such factors using geotechnical analysis, rock mechanics, and computer modeling. Berghead's builders achieved practical solutions without any of these technologies. Whether this knowledge emerged through generations of observation or through specialized expertise remains unknown. Perhaps the most famous mystery of Berghead centers on the carved bull stones. Approximately 30 carved sandstone slabs depicting bulls have been documented, making them among the most distinctive examples of Pictish art ever discovered. The carvings display remarkable consistency in proportions, style, and execution. This raises a significant question. Were these images created by a small group of highly trained specialists? If so, Berghead may have supported an organized workshop comparable to artistic centers elsewhere in Europe. Alternatively, the consistency could indicate the use of standardized design methods or measurement systems. Some researchers have noted that repeating complex artistic motifs with such accuracy generally requires established techniques for transferring designs onto stone. The bulls themselves remain mysterious. No surviving text explains their meaning. They may represent royal authority, religious symbolism, clan identity, military power, or something entirely different. More than a century of research has failed to produce a universally accepted interpretation. The site's most extraordinary surviving structure may be the Berghead Well. Hidden beneath the modern town, this underground chamber descends through a series of stone steps into a water-filled reservoir carved into bedrock. The well was not discovered until 1809 during construction work and remains one of the finest examples of early medieval water engineering in Britain. The technical challenges involved were considerable. Builders had to identify reliable groundwater sources, calculate excavation depths, prevent collapse, and create long-term access to the water supply. The staircase itself descends deep into the earth through carefully constructed masonry. Such work required planning, surveying, and precise execution. What remains unclear is the purpose of the structure. Some archaeologists argue it served as a practical water source for the fort's inhabitants. Others suggest ceremonial or religious functions. Water played an important role in many ancient belief systems, and the well's unusual design may indicate ritual significance. If this interpretation is correct, Berghead's builders devoted substantial engineering resources to symbolic activities rather than purely practical needs. Another unresolved question concerns Berghead's role within the wider Pictish world. Archaeological evidence suggests the site functioned as a major power centre. Imported goods discovered in the region indicate participation in extensive trade networks connecting northern Britain with Ireland, Scandinavia, and continental Europe. Its position overlooking the Moray Firth may have provided control over important maritime routes. If Berghead served as a naval hub, its strategic significance would have been enormous. Yet almost no direct evidence survives regarding Pictish fleets, shipbuilding practices, or maritime administration. This creates a paradox. The location strongly suggests maritime importance, but the supporting records have largely vanished. The arrival of the Vikings adds another layer of mystery. Historical sources record Viking activity throughout northern Scotland during the 9th century. Some archaeologists believe Berghead may have been attacked or destroyed during this period. Excavations have revealed evidence of burning and destruction that could correspond to violent conflict. Yet certainty remains elusive. The archaeological record cannot conclusively identify who caused the damage or precisely how events unfolded. If Vikings were responsible, Berghead raises another important question. How did attackers overcome one of the strongest fortifications in Pictland? Was the site captured through military force, internal political collapse, economic decline, or a combination of factors? What do you think is the greatest mystery of Berghead Fort? The massive coastal engineering, the underground well, or the lost knowledge of the Picts? Share your thoughts in the comments below. Perched more than 300 metres above sea level in the Clwydian range of northeast Wales, Moel y Gaer overlooks the Vale of Clwyd and commands sweeping views across northern Wales. Archaeologists believe this ancient hill fort was occupied during the Iron Age, roughly between 800 BC and the Roman conquest of Britain. At first glance, it appears to be little more than a ring of ancient earthworks on a hilltop. Yet modern surveys, excavations, and landscape analysis reveal a far more intriguing story. Hidden within its banks and ditches are clues to engineering skills, environmental knowledge, and organizational abilities that remain only partially understood. More than 2,000 years after its construction, Moel y Gaer continues to raise questions that modern archaeology cannot fully answer. The site was recognized as an ancient monument during 19th century surveys of the Clwydian Hills, but systematic archaeological investigation developed gradually. Aerial photography, topographic mapping, geophysical surveys, and modern LiDAR scanning have since revealed details invisible from ground level. These technologies showed that Moel y Gaer was not an isolated structure, but part of a larger network of hill forts spread across the Clwydian range. What researchers discovered was not merely a defensive enclosure, but evidence of a sophisticated understanding of terrain, construction, and regional communication. The first mystery begins with location. Modern military planners rely on satellite imagery, digital terrain models, and computer simulations to identify strategic positions. The builders of Moel y Gaer possessed none of these technologies, yet they selected one of the most effective defensive locations in the region. From the summit, visibility extends across major natural routes running through northeast Wales, allowing anyone moving through the Vale of Clwyd to potentially be observed from the fort. Researchers studying visibility patterns have noted that the site occupies a position offering exceptional surveillance while remaining difficult to approach. This raises an obvious question. How did Iron Age builders determine the optimal location? The answer may seem simple. They climbed hills and looked around. However, choosing the best position among dozens of possible locations across a complex landscape is far more challenging than it appears. Modern viewshed analysis demonstrates that relatively small differences in elevation can dramatically affect visibility. The builder somehow identified a position that maximized observation while also providing access to water, grazing land, and transportation routes. Whether this resulted from generations of accumulated knowledge or deliberate large-scale surveying remains unknown. The second mystery involves the earthworks themselves. The defensive banks surrounding Moël Guerre may appear modest compared with stone fortifications such as those found in later Roman forts. Yet constructing them required an enormous amount of labour. Archaeological measurements indicate that thousands of cubic meters of earth and stone were moved to create the ramparts and ditches. Depending on the exact methods used, this could represent tens of thousands of individual labour hours. To appreciate the scale of this achievement, consider a comparison. A single cubic metre of compacted soil can weigh between 1.5 and 2 metric tons. Moving thousands of cubic metres without machinery would require a highly organised workforce. Every basket of soil had to be excavated, transported, and placed with precision. Every section of ditch required planning, and every rampart required stabilisation. Yet no written instructions survive. The builders left behind the finished structure but not the engineering knowledge that created it. The third mystery concerns structural durability. Moël Guerre has endured more than 2 millennia of wind, rain, frost, erosion and vegetation growth. Wales experiences some of the wettest conditions in Britain, and over centuries water gradually destroys poorly designed earthworks. Yet large portions of the fortification remain visible today. This survival suggests a sophisticated understanding of drainage and slope stability. Modern civil engineers use soil analysis, computer modelling, and geological surveys when designing large earthworks. Iron Age builders possessed none of these tools. Nevertheless, many sections of the ramparts continue to retain their form after approximately 2,000 years of exposure. How did they know which soils would remain stable? How did they manage water runoff? How did they prevent catastrophic collapse? Archaeologists can observe the results, but the practical techniques behind them remain largely speculative. The fourth mystery involves geology. Detailed surveys suggest that the builders exploited natural terrain with remarkable efficiency. Rather than imposing an artificial design onto the landscape, they integrated defensive structures into existing slopes and ridges. Steeper natural gradients were incorporated into the defensive system, reducing the amount of construction required. This approach resembles a principle used in modern military engineering: maximize natural advantages while minimizing labor costs. The problem is that such decisions require an accurate understanding of terrain. Today, engineers evaluate slope angles using instruments, whereas Iron Age builders relied entirely on observation and experience. The consistency with which hill forts across Britain exploit topography has led some researchers to argue that a sophisticated body of practical landscape knowledge once existed. If so, that knowledge disappeared long ago. The fifth mystery concerns communication. Moël Guerre was not alone. Several other hill forts occupy prominent positions along the Clwydian range, and many are visible from one another, creating the possibility of an interconnected observation network. This raises fascinating questions. Could signals have been transmitted between hill forts? Could warning messages have travelled across large distances using fire or smoke? Could communities have coordinated responses to threats through visual communication? Comparable systems existed elsewhere in the ancient world. Classical Greek states used beacon chains. Roman military forces employed signalling stations, and medieval kingdoms later developed similar warning networks. The challenge is that almost no direct evidence survives for how communication functioned in Iron Age Wales. The geography suggests the possibility, but the archaeology remains inconclusive. The sixth mystery concerns life inside the enclosure. Geophysical surveys indicate that Moel Iger was more than a refuge used only during emergencies. Evidence suggests repeated occupation and organised activity within the fort. The arrangement of internal spaces appears structured rather than random. This raises an important question: who designed the settlement? Planning a hilltop community requires decisions about housing, storage, movement, defence and resource management. These considerations resemble challenges faced by urban planners today, albeit on a smaller scale. The existence of organised layouts suggests that at least some individuals possessed specialised knowledge about settlement design. Yet their identities, methods and training remain unknown. The seventh mystery involves labour organisation. Archaeologists often focus on structures, but every structure represents human coordination. To build Moel Iger, workers had to gather materials, transport resources, prepare foundations, construct defences, and maintain the site. Food had to be supplied, tasks had to be assigned, and work had to be coordinated. Modern project management relies on written plans and records, whereas Iron Age societies relied entirely on memory and oral communication. This raises one of the most difficult questions in archaeology. How were large construction projects organised in societies that left few written documents? The answer remains elusive. The eighth mystery is the relationship between Moel Iger and broader developments in Iron Age Britain. Across Britain, hill forts emerged during a period of significant social change. Some became political centres, others functioned as economic hubs, and a few developed into major population centres. Moel Iger belongs to this wider phenomenon, yet its exact role remains debated. Was it primarily a fortress, a ceremonial centre, a symbol of authority, a refuge during conflict, or perhaps all of these simultaneously? Different interpretations produced very different pictures of the society that built it. Perched approximately 485 metres above sea level on the northern slopes of Yr Eifel in northwestern Wales, Tre'r Ceiri overlooks the Llyn Peninsula, the Irish Sea, and vast stretches of the surrounding landscape. This ancient hill fort is among the most impressive surviving Iron Age settlements in Britain, yet it remains one of the least understood. Archaeologists estimate that the fortress was occupied between roughly the 1st century BC and the 2nd century AD. What makes Tre'r Ceiri extraordinary is not simply its age, but the remarkable level of engineering displayed by a community that left behind no written records explaining how it accomplished such a feat. The discovery of Tre'r Ceiri was never dramatic. Local people had known about the ruins for centuries, but systematic archaeological investigations during the 19th and 20th centuries revealed the true scale of the site. Excavations uncovered the remains of approximately 150 stone-built round houses enclosed within massive defensive walls. These findings transformed Tre'r Ceiri from a local curiosity into one of the most important Iron Age settlements in Britain. Yet every excavation seemed to create more questions than answers. The first mystery begins with the fortress itself. Tre'r Ceiri occupies a mountain summit that appears highly impractical for large-scale settlement. Everything needed for construction had to be transported uphill. Stone, timber, food, water, and supplies all required tremendous effort to move across steep terrain. Modern visitors often struggle to reach the site carrying only basic equipment, yet nearly 2,000 years ago, an entire community successfully built and maintained one of the largest hill fort settlements in Wales. The defensive walls alone represent a significant engineering challenge. The outer enclosure stretches for nearly 1 kilometre around the summit, and in some areas the walls remain over 3 metres thick and more than 3 metres high. Archaeologists estimate that thousands of tons of stone were required for construction. Unlike Roman forts, which often relied on standardized plans and documented engineering methods. Tre Seri was built entirely without surviving blueprints or written instructions. The builders left no explanation of how labor was organized, how materials were transported, or how construction was coordinated. This raises an obvious question. How did Iron Age builders move such enormous quantities of stone up a mountain without advanced machinery? The mystery becomes even more fascinating when compared with other ancient construction projects. The builders of Stonehenge transported stones weighing up to 25 tons across distances exceeding 200 kilometers, while the creators of the Great Pyramid moved approximately 2.3 million stone blocks. Tre Seri operated on a smaller scale, but its mountain location created a unique logistical challenge because every stone had to be moved uphill through difficult terrain. Researchers have proposed various possibilities. Human labor alone may have been sufficient if hundreds of workers participated. Wooden sledges, rollers, ropes, and simple mechanical systems may also have been employed. However, direct evidence for these methods has never been found at the site, and the exact techniques remain unknown. The second mystery involves the fortress walls themselves. Tre Seri was constructed using dry stone masonry, a technique that relies entirely on carefully positioned stones without mortar or cement. Modern engineers understand the basic principles behind such structures, where stability comes from gravity, friction, weight distribution, and precise placement. Yet understanding the theory is not the same as understanding the execution. The walls of Tre Seri have survived nearly 2 millennia of harsh Welsh weather. The site experiences heavy rainfall, strong Atlantic winds, seasonal freezing, and repeated cycles of erosion. Despite these conditions, substantial sections remain standing. Many modern retaining walls constructed with contemporary materials require extensive maintenance after only a few decades, whereas Tre Seri's builders achieved a lifespan measured in centuries. This raises another mystery. How did Iron Age masons determine which stones belonged where? No written manuals survive. No measurement systems have been identified, and no training records exist. The practical knowledge that guided construction appears to have vanished entirely. Experimental archaeologists attempting to recreate ancient dry stone techniques frequently discover that experience matters more than formulas. Small changes in stone selection can dramatically influence long-term stability. The builders of Tre Seri clearly possessed expertise acquired over generations, yet the source of that expertise remains unknown. The third mystery concerns urban planning. Within the walls lie the remains of roughly 150 roundhouses, making Tre Seri one of the densest Iron Age settlements known in Britain. Archaeological surveys reveal that these structures were not scattered randomly across the mountain summit. Instead, they appeared arranged according to an organized plan. Clusters of houses occupy specific areas, pathways connect different sections, open spaces separate groups of structures, and certain locations seem reserved for communal activities. This organization suggests deliberate planning rather than gradual, uncontrolled growth. The problem is that archaeologists do not know who performed that planning. Did a central authority determine where houses could be built? Was there a ruling elite overseeing development? Did builders use surveying techniques now lost to history? Modern planners rely on maps, measurements, and digital models. The people of Tre Seri possessed none of these technologies. Nevertheless, they created a settlement capable of housing hundreds of residents while maintaining order within a confined mountaintop environment. The fourth mystery involves environmental engineering. The summit of Tre Seri is exposed to some of the most challenging weather conditions in the region. Winds arriving from the Irish Sea can be powerful, rainfall is frequent, and temperatures fluctuate dramatically throughout the year. Yet the settlement appears carefully adapted to these conditions. Many structures occupy naturally sheltered positions. The walls follow contours that maximize protection while minimizing exposure. Drainage appears integrated into the landscape, and certain house foundations were positioned to take advantage of terrain features that reduced environmental stress. Today, architects use computer simulations to analyze wind patterns and thermal performance. The builders of Tre Seri relied entirely on observation and accumulated experience. This raises an important question. How sophisticated was their environmental knowledge? Some researchers argue that ancient communities often possessed a deeper practical understanding of local ecosystems than modern observers assume. Tre Seri may represent one of the clearest examples of such expertise. The fifth mystery concerns defense. Hill forts are traditionally interpreted as military structures, and Tre Seri certainly possessed formidable defensive advantages. The mountain location provided visibility across vast distances. Approaching enemies could be detected long before arrival, and the walls created multiple layers of protection. Yet some archaeologists question whether defense alone explains the site's existence. The resources required for construction were enormous, and maintaining hundreds of residents on a mountain summit demanded continuous logistical effort. If military security was the sole objective, less demanding locations might have provided similar protection. This has led to alternative theories. Tre Seri may have functioned as a political center, a symbol of power, a ceremonial location, or a combination of all three. Similar debates surround hill forts across Europe. Sites once viewed purely as fortresses increasingly appear to have served complex social functions. The true purpose of Tre Seri remains uncertain. The sixth mystery involves population and organization. Archaeologists estimate that several hundred people may have lived within the enclosure during periods of peak occupation. Sustaining such a population required food production, resource management, construction expertise, and social coordination. This implies a level of organizational complexity often underestimated in Iron Age societies. Comparison with contemporary Europe is revealing. During the first centuries BC and AD, Roman engineers were constructing roads, aqueducts, bridges, and military fortifications across Britain and continental Europe. Tre Seri's builders lacked Roman technology and written administration, yet they successfully created a large-scale settlement adapted perfectly to its environment. How was labor organized? How were skills transmitted? How were large construction projects coordinated? These questions remain unanswered,